Somewhere out there, right now, a rock the size of a small mountain is hurtling through the darkness of space at nearly 15 kilometers per second. It has no mind. It has no malice. It does not care about the cities below, the oceans, the billions of lives clinging to a thin shell of atmosphere wrapped around a fragile blue world. It is just a rock. And in roughly 850 years, it may collide with Earth with the force of tens of billions of tons of TNT. Not a metaphor, not a science fiction scenario. A mathematically calculated possibility that has earned its place in the most exclusive and terrifying catalogue in all of science. A list of objects that might end civilization as we know it. The asteroid is called 1950 DA. It was first spotted in 1950 by an astronomer at the Lick Observatory in California, tracked for just 17 days and then lost. For half a century, it drifted unseen through the inner solar system, crossing Earth's orbital path again and again, invisible to the civilization it might one day destroy. Then, on the very last night of the year 2000, a survey telescope in New Mexico found it again. And when astronomers calculated its orbit with modern precision, they discovered something that made the room go quiet. This object, roughly 1.1 kilometers across, was on a trajectory that brought it uncomfortably close to its orbital path on one specific date. The 16th of March, in the year 2880. The probability of impact was not zero. That might sound distant. 850 years. Surely that is someone else's problem. Surely by then humanity will have colonized Mars, developed warp drives, evolved into something unrecognizable. But here is the uncomfortable truth that planetary defense scientists have been warning about for decades. A truth that most people never hear. The physics of deflecting an asteroid this size does not get easier with time unless you start early. Very, very early. And right now, humanity does not possess a proven method for redirecting a 1-kilometer wide object. In 2022, NASA's DART mission successfully nudged a tiny moonlet called Dimorphos, roughly 160 meters across, by a few millimeters per second. It was a milestone, a proof of concept, and Dimorphos is roughly 7 times smaller than 1950 DA and hundreds of times less massive. The difference in scale between those two objects is like the difference between pushing a shopping cart and pushing an aircraft carrier. Same principle. Radically different engineering. If 1950 DA strikes Earth, the energy released would be approximately 60,000 megatons of TNT equivalent. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, yielded 50 megatons. 1950 DA would deliver more than 1,000 times that energy in a single instant. An impact winter would follow, a shroud of dust and debris lofted into the stratosphere, blocking sunlight for years, collapsing global agriculture, triggering famine on a scale that makes every historical catastrophe look minor. Billions would die, not from the impact itself, but from the cold and the hunger that follow. Coastal cities would be obliterated by tsunamis if the asteroid struck the ocean. Continental interiors would be scorched by firestorms if it struck land. The civilization that existed before the impact and the civilization, if any, that existed after would be unrecognizable to each other. And yet almost nobody talks about it. If you asked 1,000 people on the street to name the biggest long-term threats to human existence, you would hear climate change, nuclear war, artificial intelligence, perhaps a pandemic. Almost no one would say asteroid, and yet asteroids are the only natural threat capable of ending civilization in a single afternoon. Not slowly, over generations, in one day, one object, one collision. What makes 1950 DA particularly unsettling is not just the impact date or the probability, it is what we do not know about it. The asteroid spins so rapidly, completing a full rotation in just 2.12 hours, that conventional physics says it should fly apart. At that rotation rate, the centrifugal force at the equator nearly exceeds the gravitational pull holding the surface material down. For most asteroids of this size, which are thought to be loosely bound piles of rubble rather than solid monoliths, spinning this fast would be fatal. The material would simply drift away, and the asteroid would disassemble. But 1950 DA has not disassembled. Something is holding it together, some force beyond gravity, and we do not yet know what that force is. Cohesive attraction between dust grains, van der Waals forces at the molecular level. internal friction, perhaps an unusual composition. Whatever it is, it changes everything about how you might try to deflect this object. If you push a solid rock, you get one result. If you push a loosely bound pile of rubble, held together by the weakest of forces, you might get something entirely different. You might shatter it. You might scatter it. You might replace one large threat with dozens of smaller ones, each still capable of devastating a continent. And there is another layer of uncertainty that makes 1950 DA unlike any other threat humanity has faced. The asteroid's future orbit is not determined solely by gravity. Heat plays a role. Every asteroid absorbs sunlight on its day side and radiates that heat into space as infrared radiation. This process creates a tiny but relentless thrust called the Yarkovsky effect, named after a Russian engineer who first described the phenomenon in the 1800s. Over years, the effect is negligible. Over centuries, it accumulates. Over 850 years, it could shift 1950 DA's position by thousands of kilometers, the difference between a clean miss and a direct hit. And we cannot yet measure the Yarkovsky effect on this asteroid with the precision needed to resolve that ambiguity. The data simply does not exist yet, so here is the situation. Humanity is aware of an object that could end civilization on a specific date. The probability is not high, currently estimated at roughly 1 in 8,300, but it is not zero. The object's internal structure is poorly understood. The forces holding it together are unknown. Its future orbit is blurred by thermal effects we cannot yet quantify. The methods available to deflect it have never been tested at the required scale, and the political, economic, and psychological barriers to mounting a centuries-long defense program are staggering. By the end of tonight, you are going to understand exactly what 1950 DA is, why it behaves in ways that challenge our best models, what the impact would do to Earth, what options exist for stopping it, and why the greatest threat is not the asteroid itself, but our own inability to act on dangers that feel far away, right up until the moment they arrive. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand why a single rock in space can threaten an entire civilization, you first need to understand the neighborhood we live in. And the neighborhood is not as safe as it looks. Picture the solar system. Most people imagine it as a neat arrangement of planets orbiting the sun, each in its own lane, well-spaced and orderly. That image is a lie. The solar system is not a clockwork mechanism. It is a shooting gallery. Between the planets, around the planets, and crossing the orbits of the planets, there are millions upon millions of rocky and metallic objects left over from the formation of the solar system 4.6 billion years ago. These are the asteroids, the comets, the fragments, the debris. They range in size from grains of dust, smaller than a pinhead, to dwarf planets, nearly 1,000 kilometers across. Some orbit peacefully in the asteroid belt between Mars and Jupiter. Others have been gravitationally perturbed into eccentric orbits that cross the paths of the inner planets, including Earth. These are called near-Earth objects, and as of the mid-2020s, more than 34,000 of them have been discovered and catalogued. Most are small, most will never come close enough to matter, but the sheer number should give you pause. 34,000 known objects, and that count grows by hundreds every year as survey telescopes with ever greater sensitivity sweep the skies and find things that were always there but too faint or too small to detect. How many remain undiscovered? NASA estimates that the survey of near-Earth asteroids larger than 1 kilometer is more than 90% complete. That sounds reassuring until you realize what the remaining 10% means. 10% of the 1 kilometer and larger population could be 50 to 100 objects, any one of which is capable of causing a global catastrophe, drifting undetected through the inner solar system right now. And for smaller asteroids, those in the 100 to 500 meter range that could still devastate a continent or trigger a regional catastrophe, the completeness drops dramatically. Less than half of those objects have been found. The sky, to put it plainly, is full of things we have not seen yet. But let us not think about what we have not found. let us think about what impacts have done in the past, because the history of Earth is not a peaceful story. It is a history of collisions. The most famous impact in Earth's history struck what is now the Yucatan Peninsula of Mexico, approximately 66 million years ago. The Chicxulub impactor, as it is known, was a body roughly 10 to 15 kilometers in diameter, traveling at perhaps 20 kilometers per second. When it hit, the energy released was on the order of 100 trillion tons of TNT. To put that in perspective, if you took every nuclear weapon ever built by every nation on Earth, combined them all, and detonated them simultaneously, the total yield would still be a tiny fraction of the Chicxulub impact. The asteroid did not just make a hole, it fundamentally altered the planet. The impact created a crater roughly 180 kilometers in diameter and 30 kilometers deep. Trillions of tons of rock were vaporized instantly, launching a plume of superheated debris into space, some of which re-entered the atmosphere on the far side of the planet, igniting forests on every continent. The blast wave circled the globe. Mega tsunamis swept across the Gulf of Mexico and the Atlantic. Earthquakes of magnitude 10 or greater shook the crust, and then came the darkness. Dust and sulfur compounds lofted into the stratosphere created a shroud that blocked sunlight for months, possibly years. Photosynthesis collapsed. The food chain disintegrated. 75% of all species on Earth went extinct, including every non-avian dinosaur, creatures that had dominated the planet for more than 160 million years. They were gone in what geologists consider an eye blink, a transition so abrupt that you can find it in the rock record as a thin dark line, a layer of clay enriched with iridium, an element rare on Earth's surface but common in asteroids. That line, a few centimeters thick, is the signature of the end of a world. But Chicxulub was not unusual. It was merely the most recent mass extinction level impact. The geological record is littered with scars from earlier collisions. The Vredefort impact structure in South Africa, roughly 2 billion years old, was created by an object estimated at 10 to 15 kilometers in diameter. The Sudbury Basin in Ontario, Canada, is the remnant of an impact roughly 1.8 billion years ago by a body of similar size. The Poppyguy crater in Siberia, about 35.7 million years old, was formed by a 5 to 8 kilometer asteroid, an impact that generated diamonds from the carbon in the target rock. The Manicouagan crater in Quebec, about 214 million years old, is now a circular lake more than 70 kilometers across, visible from space, a permanent monument to the violence of the solar system. These are the ones we can still see. Plate tectonics, erosion, and sedimentation have erased countless others. Earth's surface is constantly being recycled. The ocean floor is entirely replaced every 200 million years or so. Continental surfaces are worn down by wind and water. The true number of major impacts in Earth's 4.6 billion year history is unknowable, but it is certainly far larger than the handful of surviving craters suggest. The planet has been hit and hit hard, over and over again, and it will be hit again. The only question is when. If you could compress Earth's entire history into a single 24-hour day, with the planet forming at midnight and the present moment at the following midnight, life first appears around 4 in the morning. Complex multicellular life does not emerge until after 8:30 in the evening. The dinosaurs reign from about 10:45 at night until roughly 11:39, and human civilization, all of recorded history, every empire, every invention, every person who has ever lived, occupies the last fraction of the last second before midnight. In that compressed day, civilization-threatening impacts have occurred roughly every few hours. We are, in a statistical sense, living on borrowed time, not because an impact is imminent in any given year, but because the process is ongoing, and our window of safety is not guaranteed to last. This is the context in which the story of 1950 DA unfolds. Not as an anomaly, but as a reminder. The solar system is not done with Earth yet. The discovery of 1950 DA begins with a man named Carl Wittinen, an astronomer at the Lick Observatory on Mount Hamilton, east of San Jose, California. In February of 1950, Wittinen was working through a routine observing run, scanning the sky with photographic plates, the standard tool of the era. The plates were large glass panels coated with light-sensitive emulsion, exposed for minutes at a time through the telescope's optics. Stars appeared as points, planets appeared as brighter points, and anything that moved during the exposure appeared as a short streak, its motion betraying its proximity to Earth. On the night of February 23rd, Wirtanen found such a streak, a faint trail of light cutting across the fixed stars, indicating a nearby object in solar orbit. It was not a comet. It had no tail, no coma, no fuzzy glow of outgassing material. It was a solid body, a rock, reflecting sunlight as it passed through the inner solar system. The object was designated 1950 DA, following the provisional naming conventions of the era. Over the next 17 days, astronomers at Lick and other observatories tracked its position, measuring its changing location against the background stars to compute a preliminary orbit. The data showed an object with a semi-major axis of about 1.7 astronomical units, meaning its average distance from the Sun was about 1.7 times Earth's distance. Its orbit was eccentric enough to cross Earth's orbital path, bringing it into the inner solar system periodically. The object was clearly a near-Earth asteroid, but with only 17 days of observations and the limited precision of photographic astrometry, the orbit was not well constrained. The uncertainties were large, and then the asteroid moved beyond reach of the telescopes, grew too faint to detect, and was lost. For the next half-century, 1950 DA was a ghost, a name in a catalogue, a set of approximate orbital elements. No one knew exactly where it was. No one was looking. The technology to conduct comprehensive surveys of near-Earth space did not yet exist. Asteroid science was a backwater, a niche field pursued by a small community of dedicated researchers, while the rest of astronomy focused on galaxies, quasars, and the expanding universe. The idea that an asteroid might threaten Earth was considered fringe, almost disreputable. The Cold War was producing threats that felt far more immediate, and so the rock drifted, unseen and untroubled, orbiting the Sun in its steady elliptical path, crossing Earth's orbit roughly every few years, a train running on schedule through a station where no one was watching. Then came the night of December 31st, 2000, the last night of the 20th century. At the Lincoln Near-Earth Asteroid Research Facility in New Mexico, known by its acronym LINEAR, an automated survey telescope was scanning the sky as it did every clear night, recording the positions of faint moving objects. LINEAR was one of the most prolific asteroid discovery programs in history, operated by MIT's Lincoln Laboratory for the United States Air Force. Its primary purpose was to detect and catalogue near-Earth objects, feeding data into the growing global inventory of potential hazards. That night, the system detected an object moving through the constellation Canis Major. It was relatively bright, suggesting a significant size, and its motion indicated a near-Earth orbit. Over the following nights and weeks, additional observations refined the object's orbit. And then someone did what astronomers always do with a newly discovered object. They checked the old records. They compared the newly computed orbital elements with the catalogue of lost asteroids, objects that had been observed once and then vanished. The match was unmistakable. The object LINEAR had found was 1950 DA. The ghost had returned. But this time, humanity had tools that Carl Wirtanen could not have imagined. Radar. In March of 2001, 1950 DA made a moderately close approach to Earth, passing within roughly 7.8 million kilometers, about 20 times the Earth-Moon distance. In everyday terms, that is an enormous gap. In astronomical terms, it is a whisper, and it was close enough for radar. Scientists at the Goldstone Deep Space Communications Complex in the Mojave Desert, part of NASA's Deep Space Network, and at the Arecibo Observatory in Puerto Rico, the massive 305-meter radio dish nestled in a karst sinkhole aimed their transmitters at the asteroid and fired pulses of microwave energy. The pulses travelled outward at the speed of light, struck the asteroid and bounced back. From the time delay and the Doppler shift of the return signal, scientists could measure the asteroid's distance and velocity with extraordinary precision, far beyond what optical telescopes could achieve. But radar gave them more than just position and speed. It gave them shape and spin. By analysing how the return signal varied over time as different parts of the asteroid rotated into and out of view, researchers could reconstruct a rough three-dimensional model of the object, and the picture that emerged was striking. 1950 DA was an irregularly shaped body, roughly 1.1 kilometers in its longest dimension, tumbling through space with a rotation period of just 2.126 hours. That is one full spin every 2 hours and 7 minutes. That number might seem unremarkable. It is not. It is one of the most important measurements ever made in asteroids science, and its implications reach far beyond the question of whether this particular rock will hit Earth. To understand why, you need to understand a concept called the spin barrier. Every object in space that is held together by its own gravity has a maximum rotation speed. Spin it any faster, and the centrifugal force at the equator exceeds the gravitational attraction pulling the material inward. The surface material lifts off. The object begins to shed mass, to elongate, to disassemble. For a typical asteroid with a density of about 2 grams per cubic centimeter, this limit corresponds to a rotation period of roughly 2.2 hours. Anything faster, and the object comes apart, unless it is a single solid monolith with internal strength like rock or iron, in which case it can spin faster because its structural integrity holds it together. The vast majority of asteroids larger than about 200 meters are not monoliths. They are rubble piles, collections of fragments loosely bound by gravity, the result of ancient collisions that shattered precursor bodies and then allowed the fragments to reaccumulate under their mutual gravitational attraction. You can think of them as enormous piles of gravel, held together not by cement but by the feeble gravity of their own mass. These rubble pile asteroids universally obey the spin barrier. No rubble pile larger than 200 meters has ever been observed spinning faster than the 2.2-hour limit. It is one of the cleanest empirical boundaries in all of asteroid science. And then there is 1950 DA, spinning at 2.12 hours, right at the edge, almost exactly at the limit. This immediately raised a question that has occupied asteroid scientists for more than 2 decades. Is 1950 DA a monolith, a single solid piece of rock or metal, surviving intact from the early solar system? Or is it a rubble pile, like almost every other asteroid its size, but somehow held together by forces beyond gravity? The answer matters enormously. If it is a monolith, deflection strategies that involve impacting it, pushing it, or detonating a device near it become more predictable. Solid bodies respond to impulse in straightforward ways. If it is a rubble pile held together by cohesive forces, the situation is far more complex. A kinetic impactor might bury itself in the surface without transmitting significant momentum to the bulk. A nuclear detonation might blow off a shell of material while leaving the core trajectory unchanged. A gravity tractor would still work, in principle, but with uncertainties in the mass distribution that make precision maneuvering difficult. The radar data from 2001, combined with thermal observations from infrared telescopes, suggested that 1950 DA's density is relatively low, roughly around 1.7 to 2 grams per cubic centimeter. That is consistent with a rubble pile, not a solid monolith. A solid iron-nickel asteroid would have a density closer to 8 grams per cubic centimeter. Even a solid stony asteroid would be around 2.5 to 3. The low density implies porosity, internal voids, loosely packed material. It implies a rubble pile. But a rubble pile spinning at 2.12 hours should not exist. And yet it does. That contradiction, sitting quietly at the heart of asteroid science, tells us something important. Either our understanding of rubble pile physics is incomplete, or there are forces at work inside 1950 DA that we have not accounted for. Cohesive forces between grains, the same van der Waals attractions that allow a gecko to walk up a glass wall, might be sufficient to provide the extra binding needed to survive the spin. Laboratory experiments on simulated asteroid regolith have shown that very fine-grained material can exhibit significant cohesive strength, enough to allow a rubble pile to spin faster than gravity alone would permit. But extrapolating laboratory results to a 1-kilometer body in the vacuum of space, across centuries of thermal cycling and micrometeorite bombardment, is uncertain territory. We do not know with confidence what is happening inside 1950 DA, and that ignorance is not academic, it is operational. It determines what we can do about it. With the new radar data, John Giorgini at NASA's Jet Propulsion Laboratory set about refining the asteroid's orbit. He now had two sets of observations separated by 51 years. The 17 days of photographic data from 1950 and the precise radar ranging from 2001. That 51-year baseline, combined with the exquisite precision of radar astrometry, allowed him to project the orbit forward with far greater accuracy than had ever been possible. And when he ran the trajectory forward through centuries of orbital evolution, accounting for the gravitational perturbations of every major planet and hundreds of smaller bodies, he found a date. March 16th, 2880. On that date, the nominal orbit, the best fit trajectory, passed through a region of space that overlapped with Earth's position. The probability of impact, calculated from the range of orbital uncertainties, was approximately 1 in 300. 1 in 300. That number hit the planetary defense community like a shockwave. At the time of publication, in 2002, no other known asteroid had a probability of impact anywhere close to that value for a specific future date. On the Palermo Technical Impact Hazard Scale, a logarithmic measure that compares the impact risk of an asteroid to the background risk from all undiscovered objects, 1950 DA scored higher than any other object ever assessed. It was, by the cold mathematics of orbital mechanics, the most threatening known object in the solar system. The response from the scientific community was careful, deliberate, and profoundly aware of the need to communicate accurately. The key paper, authored by Giorgini and colleagues, was published in the journal Science in April 2002. It laid out the orbital analysis, the impact probability, and, critically, the reasons for uncertainty. The Yarkovsky effect, the tiny thermal thrust created by the asteroid's absorption and re-radiation of sunlight, was identified as the single largest unknown. Without a precise measurement of this effect for 1950 DA, the long-term orbital prediction could not be refined further. The paper was a model of responsible scientific communication, clear about the threat, honest about the uncertainties, and explicit about what needed to be done next. Subsequent observations, including additional radar data from later close approaches and improved modeling of the Yarkovsky effect, have revised the impact probability downward. As of the most recent assessments in the 2020s, the probability stands at approximately 1 in 8,300. That is lower than the initial estimate, and it represents progress. But it is not zero. And in a field where the consequences of being wrong are measured in billions of lives, not zero carries a weight that no amount of statistical context can lighten. The foundation is set. The asteroid is real, the orbit is real, the probability is real, the uncertainties are real, and the challenge of doing something about it, across a timespan that dwarfs any project humanity has ever undertaken, is the most profound test of foresight our species has ever faced. But here is what makes this truly terrifying. The window to act may be far shorter than 850 years, and the reasons for that have everything to do with the physics of deflection, the politics of long-term planning, and a deeply human tendency to ignore problems that feel far away, right up until the moment they are too close to stop. But to truly appreciate the danger that objects like 1950 DA represent, it helps to understand how close Earth has come to catastrophe in the recent past, not in geological time, but within living memory. On February 15, 2013, a small asteroid entered Earth's atmosphere over the city of Chelyabinsk in central Russia. The object was roughly 20 meters across, a tiny speck by the standards of the near-Earth population, invisible to every survey telescope on the planet because it approached from the direction of the sun, where ground-based telescopes cannot look. It struck the atmosphere at approximately 19 kilometers per second, compressing the air ahead of it into a blazing shock front that heated to temperatures hotter than the surface of the sun. The resulting fireball was brighter than the sun itself, visible from hundreds of kilometers away. As the object descended, it broke apart, releasing energy equivalent to roughly 500 kilotons of TNT, about 30 times the yield of the Hiroshima bomb. The airburst sent a shockwave racing across the city, blowing out windows in thousands of buildings, injuring over 1,500 people, most of them cut by flying glass. Dashcam footage from across the region captured the surreal scene. A brilliant white streak crossing the morning sky, followed seconds later by a thundering boom and the crack and shatter of glass. No one was killed. The object was small. The detonation occurred high in the atmosphere, and pure luck determined that the shock wave struck a city of moderate size rather than a major metropolitan center. But the Chelyabinsk event was a wake-up call of the first order. A 20-meter object had entered the atmosphere, detonated with the energy of a substantial nuclear weapon, and injured 1,500 people, and nobody saw it coming. No warning, no detection, nothing. The first indication that an asteroid had arrived was the flash in the sky. Now multiply the energy by a factor of 120,000. That is the difference between Chelyabinsk and 1950 DA. A 20-meter rock produced 500 kilotons. A 1.1 kilometer rock would produce 60,000 megatons. The scaling is not linear, it is worse than linear, because larger objects penetrate deeper into the atmosphere before detonating, delivering more of their energy to the surface, rather than dissipating it in the upper atmosphere. A Chelyabinsk-size event is a regional incident. A 1950 DA-size event is a global catastrophe. The difference between them is the difference between a firecracker and a thermonuclear weapon. And there is another near miss that deserves attention. On June 30th, 1908, something exploded over the Podkamennaya Tunguska River in a remote region of Siberia with an energy of roughly 10 to 15 megatons. The blast flattened an estimated 80 million trees over an area of roughly 2,150 square kilometers. The shock wave was detected by barographic stations across Europe. Seismographs registered the event thousands of kilometers away. If the Tunguska object, thought to be either a small asteroid or a comet fragment, roughly 60 to 190 meters in diameter, had arrived 4 hours and 52 minutes later, Earth's rotation would have placed St. Petersburg directly in the impact zone. A city of over 1 million people would have been destroyed by an object that no one knew existed. These events, Chelyabinsk and Tunguska, are tiny compared to what 1950 DA represents. They are firecrackers compared to a bomb. But they demonstrate with cold clarity that the threat is not hypothetical. Rocks fall from space. They explode with enormous energy. They damage cities and flatten forests. And the only reason they have not yet caused a mass casualty event in modern history is luck. Pure, unearned luck. The kind of luck that cannot be relied upon across centuries. The discovery story of 1950 DA gains its urgency from this context. When Carl Vertinen spotted that faint streak on his photographic plate in 1950, he was not looking for danger. He was doing science. He was cataloguing, measuring, adding to the slowly growing body of knowledge about the small bodies of the solar system. The concept of planetary defense did not exist. The idea that an asteroid might threaten Earth was not taken seriously by the scientific mainstream. Vertinen recorded 17 days of observations, reported the object to the Minor Planet Center, and moved on. The asteroid moved beyond range of his telescope and vanished from human knowledge for 50 years. During those 50 years, the asteroid completed roughly 29 orbits of the Sun, crossing Earth's orbital path each time unseen and untracked. On at least some of those crossings, it must have passed relatively close to Earth, close enough that a modern survey telescope would have detected it. But modern survey telescopes did not exist. The Linear program, which would eventually rediscover 1950 DA, did not begin operations until 1998. The Catalina Sky Survey, another major discovery program, started in 2004. The Vera C. Rubin Observatory did not begin its survey until the mid-2020s. For most of the 20th century, the sky was essentially unmonitored for near-Earth objects. We were blind, and we were lucky. The rediscovery of 1950 DA on December 31st, 2000, was therefore not just a scientific event, it was a symbolic one. The last day of the 20th century, a century that had seen 2 world wars, the splitting of the atom, the moon landing, and the birth of the digital age, ended with the discovery that a rock from space might threaten human civilization 9 centuries into the future. It was as if the universe, on the last page of one chapter of human history, had inserted a footnote. Remember this. You are not safe. To understand why 1950 DA represents such a profound challenge, you need to understand what it means to move an asteroid. Not in theory, not in the clean equations of a physics textbook, in practice. Because in theory, deflecting an asteroid sounds almost elegant. An asteroid is on a collision course. You apply a small force. The asteroid's velocity changes by a tiny amount. Over time, that tiny change accumulates, shifting the orbit enough that the asteroid misses Earth. Problem solved. The concept fits on a napkin. The reality does not. Start with the numbers. 1950 DA is roughly 1.1 kilometers across. Assume conservatively a density of about 1.7 grams per cubic centimeter based on the radar-derived estimates. That gives a mass of roughly 1.4 billion metric tons. 1.4 billion metric tons. To put that in perspective, every human being on Earth, all 8 billion of us, has a combined mass of roughly 500 million metric tons. The asteroid weighs about 3 times as much as every living person on the planet. Now imagine trying to push all of humanity a few millimeters per second to one side. That is the scale of the problem. Except the asteroid is not standing still. It is moving at 15 kilometers per second relative to Earth. It is not cooperating. And it is 850 years away from a potential collision, which sounds like plenty of time until you do the math. Here is the math. If you want to deflect an asteroid so that it misses Earth by 1 Earth radius, roughly 6,370 kilometers, you need to change its velocity by an amount that depends on how far in advance you act. The further in advance, the smaller the velocity change needed. If you act 100 years before impact, the required velocity change is on the order of millimeters per second, a gentle nudge. If you act 10 years before impact, the required change jumps to centimeters per second. If you act 1 year before impact, you need meters per second, an enormous impulse that is essentially impossible for an object of this mass with any technology we can foresee. The numbers are striking in their implications. 100 years of lead time reduces the problem to a nudge. 10 years of lead time makes it a colossal engineering challenge. 1 year of lead time makes it hopeless. The physics is unyielding. Deflection is not about raw power, it is about timing. And timing for 1950 DA is the one thing that should be in our favor. We have 850 years. That is more lead time than any civilization has ever had for any threat. You would think that would make the problem easy. It does not, because lead time only helps if you act on it. And acting on it requires 2 things: certainty that the asteroid will actually hit, and the political will to spend enormous resources preventing an event that no one alive will ever see. 1950 DA offers neither. The certainty problem comes from the Yarkovsky effect, and it is worth understanding in detail because it is the invisible hand that makes long-range asteroid prediction so maddeningly difficult. The Yarkovsky effect works like this. An asteroid orbiting the Sun absorbs solar radiation on its sunlit side. That energy heats the surface. As the asteroid rotates, the heated surface turns away from the Sun, and the warm rock radiates that stored energy back into space as infrared light. That infrared emission carries momentum. It is tiny, almost inconceivably small, the equivalent of a few grams of thrust on a billion-ton object. But it is constant. It operates every second of every day, of every year, of every century. And like a river carving a canyon, it is the small persistent force, not the large sporadic one, that reshapes the landscape. For an asteroid like 1950 DA, the Yarkovsky effect depends on several physical properties. The surface albedo, how reflective it is, determines how much sunlight is absorbed versus reflected. The thermal conductivity, how quickly heat moves through the surface layers, determines when and where the heat is re-radiated. The rotation rate and the orientation of the spin axis determine which parts of the surface get heated, and how the thermal emission is directed relative to the orbit. And the size and shape of the asteroid determine the total area available for absorption and emission. If you know all of these properties precisely, you can calculate the Yarkovsky acceleration precisely. You can feed it into the orbital model and predict the asteroid's position centuries into the future with high accuracy. But for 1950 DA, several of these properties are poorly known. The thermal conductivity is uncertain. The exact composition of the surface is uncertain. The orientation of the spin axis has been estimated from radar data, but with significant error bars. And because the Yorp effect, a related thermal torque, can slowly change the spin rate and spin axis orientation over time, even the properties you measure today may not be valid a century from now. The result is a prediction that starts crisp and clear in the near term and becomes progressively fuzzier the further into the future you look. By 2880, the uncertainty in 1950 DA's position along its orbit is large enough to encompass both a clean miss by millions of kilometers and a direct hit. The asteroid exists in a kind of quantum superposition of outcomes, not because of any quantum physics, but because of classical uncertainty amplified by time. It will either hit or it will miss, and we cannot yet tell which. This uncertainty creates a paradox at the heart of planetary defense. The ideal time to deflect the asteroid is as early as possible, when the required force is smallest. But the ideal time to be certain about the threat is as late as possible, when the orbital prediction is most precise. These two imperatives, act early and know late, are in direct conflict. And resolving that conflict is not a physics problem. It is a decision problem, a human problem, a political problem. Consider what would happen if a government decided to act now, in the 21st century, to begin preparations for deflecting 1950 DA. The first question any politician would ask is, what is the probability? The answer today is roughly 1 in 8,300. That is higher than the background probability of a civilization-threatening impact from any random unknown object in any given century, which is perhaps 1 in several 100,000. So 1950 DA does represent an elevated threat, but 1 in 8,300 is still a small number. It means there is a 99.988% chance that the asteroid will miss Earth entirely. Spending billions of dollars to prevent an event that is 99.988% likely not to happen is a hard sell in any legislature, in any country, in any century. And yet the expected cost calculation tells a different story. If the impact would kill billions of people and end civilization, and the probability is 1 in 8,300, then the expected cost of the event, in purely mathematical terms, is enormous. Insurance companies make these calculations every day. A 1 in 8,300 chance of a loss, measured in the trillions of dollars, in the billions of lives, produces an expected value that dwarfs the cost of prevention. By any rational standard, investment in deflection capability is justified. But governments do not operate on expected value calculations. They operate on electoral cycles, on visible crises, on the urgent demands of constituents who will vote in the next election, not on the statistical preferences of descendants who will not be born for centuries. This is the first layer of the problem. The mismatch between the rational case for action and the political reality of decision-making. It has a name in risk analysis, the tyranny of the discount rate. Future costs are discounted relative to present costs. The further into the future a cost lies, the less it weighs in present decision-making. An impact in 850 years, discounted at even a modest rate, has a present value that rounds to zero. By the cold logic of economics, an impact in 2880 is not worth preventing today. The math says so. The spreadsheet says so. And the spreadsheet is catastrophically wrong, because some costs cannot be discounted. Extinction has no present value because there is no future from which to calculate it. But let us set aside the political and economic barriers for a moment and focus on the physical challenge itself, because even in a world of perfect political will and unlimited funding, deflecting 1950 DA would push the boundaries of every engineering discipline humanity possesses. The kinetic impactor approach, validated at small scale by the DART mission, is the most mature technology available. The concept is straightforward. Launch a spacecraft at high speed, aim it at the asteroid, and crash into it. The momentum transfer changes the asteroid's velocity by a tiny amount. DART struck Dimorphos at roughly 6.1 kilometers per second, and the resulting velocity change was estimated at approximately 1.7 millimeters per second, augmented significantly by the recoil effect of ejected debris. For Dimorphos, a body about 160 meters across, with a mass of roughly 5 billion kilograms, this was sufficient to change its orbital period by 32 minutes, a measurable and meaningful deflection. But scaling this to 1950 DA requires a calculation that should give pause to anyone who has ever been reassured by DART's success. 1950 DA's mass is roughly 280,000 times greater than Dimorphos's mass. To achieve the same velocity change, you would need to deliver 280,000 times more momentum. A single DART-class impactor would be completely inadequate. You would need a campaign of hundreds or thousands of impactors, or a single impactor of vastly greater mass and speed. Neither option is anywhere close to existing capability. Current launch vehicles can deliver a few thousand kilograms to deep space at most. To move a billion-ton asteroid even 1 millimeter per second using kinetic impactors, you would need to deliver millions of kilograms of impactor mass at hypervelocity speeds. That is not an incremental improvement over DART. That is a different civilization's technology. The gravity tractor concept sidesteps the impact problem entirely. Instead of hitting the asteroid, you park a massive spacecraft near it and use the spacecraft's own gravitational pull to slowly tug the asteroid off course. The beauty of this approach is its gentleness. No impact, no fragmentation risk, no uncertainty about how the surface responds to a collision. The spacecraft simply hovers nearby, maintaining a constant distance using its thrusters, and the mutual gravitational attraction between the spacecraft and the asteroid provides a slow, steady, controllable force. The problem is the scale of the required force. Gravitational attraction between a spacecraft and an asteroid is proportional to the product of their masses and inversely proportional to the square of the distance between them. For a spacecraft with a mass of 20,000 kilograms hovering about 200 meters from the surface of a billion-ton asteroid, the gravitational force is on the order of a few millinewtons. That is roughly the weight of a small mosquito on Earth's surface. To accumulate a velocity change of 1 millimeter per second on a billion-ton asteroid using a force of a few millinewtons would take, by straightforward calculation, tens of thousands of years. Even with a much larger spacecraft, say 100,000 kilograms, the timescale shrinks but remains measured in millennia. The gravity tractor is elegant but glacially slow. For 1950 DA, it is not a practical option unless we are prepared to begin operations many centuries before the impact date, and to maintain the mission continuously across that entire span. The nuclear standoff detonation is the most powerful tool in the planetary defense toolkit, and it is the only option that might be capable of deflecting a 1-kilometer asteroid with relatively short lead time. The concept involves detonating a nuclear device at a standoff distance from the asteroid's surface, not on the surface itself, but a few hundred meters above it. The nuclear radiation, primarily X-rays, is absorbed by a thin layer of surface material, which is instantly heated to millions of degrees and vaporizes outward in an expanding jet. This jet of superheated gas acts like a rocket exhaust, pushing the asteroid in the opposite direction. The impulse delivered can be orders of magnitude greater than a kinetic impactor. Simulations by researchers at Lawrence Livermore National Laboratory and Los Alamos National Laboratory have shown that a single nuclear device in the 1 megaton range, detonated optimally relative to a 1-kilometer stony asteroid, could deliver a velocity change of centimeters per second, enough to deflect the asteroid over decades of lead time. With multiple devices and optimal timing, even larger deflections are possible. But the nuclear option comes with its own set of challenges that range from the technical to the existential. The first is the uncertainty of the response. Everything we know about nuclear standoff deflection comes from computer simulations and laboratory experiments with small-scale analogues. No nuclear deflection has ever been tested on an actual asteroid. The behavior of a real asteroid surface under nuclear irradiation, the depth of energy deposition, the efficiency of mass ejection, the degree to which the impulse is transmitted to the bulk of the body, rather than lost in surface effects, all of this is uncertain. And for a rubble pile asteroid like 1950 DA, the uncertainty is compounded. A loosely bound surface might respond very differently from a solid one. The vaporized material might not form a coherent jet. The energy might dissipate into the porous interior without generating useful thrust. Or the detonation might simply break the asteroid into fragments, each one on a slightly different trajectory, spreading the impact zone rather than eliminating it. The second challenge is legal and political. The Outer Space Treaty of 1967, signed by every major spacefaring nation, prohibits the placement of nuclear weapons in space. A nuclear deflection mission would require either amending or withdrawing from the treaty, a process that would involve years of diplomatic negotiation in a context where trust between spacefaring nations is never guaranteed. The geopolitical implications of any nation launching nuclear devices into space, even for defensive purposes, are enormous. Other nations might view such a launch as a weapons test, a provocation, or a cover for military activity. The political barriers to nuclear deflection are not secondary. They may prove to be the decisive obstacle. And it gets worse, because all of these deflection methods assume that we know enough about the asteroid to choose the right approach. For a solid monolith, a kinetic impactor is relatively straightforward. For a tightly bound rubble pile, a nuclear standoff detonation might work. For a loosely bound rubble pile held together by weak cohesive forces, nothing we have developed might be adequate. And for 1950 DA, the internal structure remains fundamentally unknown. We know its size, we know its spin rate, we know its density is low, suggesting a rubble pile composition. We know it is spinning near the breakup limit, suggesting some form of cohesive binding. But we do not know the strength of that binding. We do not know the distribution of voids within the interior. We do not know whether the cohesion is uniform throughout the body or concentrated in a shell or a core. We do not know how the surface would respond to a kinetic impact, a nuclear detonation, or a sustained gravitational tug. In short, we are planning to fight an enemy we do not understand with weapons we have barely tested, on a timeline so long that the institutions planning the fight may not survive to see it through. The story of planetary defense against 1950 DA is not just a story about physics and engineering. It is a story about the limits of human foresight, the fragility of human institutions, and the peculiar tragedy of a species intelligent enough to see a threat coming, but psychologically incapable of responding to it until the danger is immediate. There is a concept in disaster preparedness called the paradox of warning. The better you are at predicting a disaster, the more time you have to prevent it, but also the more likely people are to assume it has been handled and stop worrying about it. Early warning can breed complacency rather than action, and 1950 DA is the ultimate example. 850 years of warning, the longest lead time in the history of threat assessment. And precisely because the lead time is so long, the urgency feels like zero. Compare this to the story of asteroid Apophis. When Apophis was first discovered in 2004, initial observations suggested a probability of roughly 2.7% that it would strike Earth on April 13th, 2029. 2.7%. That number was high enough to trigger immediate media attention, scientific mobilization, and public concern. Within days, additional observations refined the orbit and reduced the probability. Over the following years, the probability was further reduced, and in 2021, Apophis was removed from the risk list entirely. The system worked. The threat was identified, assessed, monitored, and resolved, all within a time frame that human attention spans could handle. A few years. The urgency was palpable. The response was swift. 1950 DA is the opposite case. The probability is lower. The timescale is vastly longer. The urgency is diffuse, spread so thin across centuries that it becomes invisible. No one panics about a 1 in 8,300 chance of something happening after their great-great-great-great-grandchildren's great-great-great-grandchildren are dead. The threat is real, but the reality does not register. And this is where the problem becomes not just difficult, but potentially unsolvable by the methods of conventional human governance. The planetary defense of 1950 DA requires something that has never existed in human history: a multi-century, multi-generational program of observation, technology development, and eventual intervention sustained across changes of government, economic collapses, wars, pandemics, and the simple corrosive passage of time. No human institution has ever maintained a focused mission of that duration. The Catholic Church is 2,000 years old, but its mission has evolved constantly. The oldest universities are about 1,000 years old, but they have reinvented themselves many times. No organization has ever held a single, specific, measurable goal for 800 years. And yet that is what planetary defense against 1950 DA requires. Something is wrong with our assumptions about how civilization handles long-term threats. We assume that awareness equals preparedness. It does not. We assume that time is our ally. It is not, unless we use it. We assume that future generations will be more capable. Perhaps they will, but capability without motivation is just potential. And motivation, for humans, requires proximity to danger. The fire must be visible before we reach for the extinguisher. There is a thought experiment that planetary defense researchers sometimes pose in quiet moments, usually late at night at conferences, when the day's presentations are over and the conversations turn philosophical. Imagine that the probability of impact were not 1 in 8,300. Imagine it were 1 in 2, 50%, a coin flip. Would that change things? Almost certainly. Governments would mobilize, funding would flow, international cooperation would materialize, driven by the existential pressure. Now imagine the probability were 1 in 100, still high enough to be terrifying, probably still enough to drive action, at least for a generation or two. Now imagine it were 1 in 1,000, 1 in 10,000, 1 in 100,000. At what point does the probability become low enough that humanity collectively shrugs and goes back to arguing about tax policy? The answer, history suggests, is surprisingly high. Even probabilities that would be considered catastrophically risky in any other domain, say 1 in 100 of losing your home to a fire, you would buy insurance, become tolerable when the timescale is long enough and the threat is abstract enough. 1 in 8,300, 8 centuries away, is well past the threshold of human concern. It is background noise, and that is precisely what makes it dangerous. But here is what makes this truly terrifying. The probability is not fixed. It will change. New observations will either increase it or decrease it. Better models will either sharpen the prediction or reveal new uncertainties. The Yarkovsky effect may push the asteroid onto a cleaner miss, or it may push it closer to a hit. We will not know until we gather more data, develop better models, and extend the observation baseline across decades or centuries. And in the meantime, the deflection window is narrowing, not quickly, but steadily. Every year that passes without action is a year that the gentle methods become slightly less effective and the violent methods become slightly more necessary. The core problem of 1950 D-Day is not the rock. It is the gap between what physics demands and what human nature provides. Physics demands early action, sustained effort, and precise knowledge. Human nature provides delayed response, episodic attention, and comfortable ignorance. And somewhere in that gap, in the space between what we should do and what we will do, a mountain of rock continues its orbit, spinning impossibly fast, held together by unknown forces, carrying the weight of a civilization's future on a trajectory we cannot yet resolve. Let us slow down and examine the impact scenario more carefully, because the details matter, and the details are worse than the headlines suggest. Most discussions of asteroid impact focus on the initial moment, the fireball, the crater, the shockwave. These are devastating, but they are local. The true danger of a 1-kilometer impactor lies in the global aftermath, and that aftermath unfolds over months and years, not seconds and minutes. When 1950 DA strikes, whether it hits land or ocean, the impact will inject vast quantities of material into the atmosphere. If it strikes land, the ejector will be primarily rock dust and soil, pulverized to fine particles by the enormous pressures of the impact. If it strikes the ocean, the ejector will include both water vapor and ocean floor sediment. In either case, the fine particulate matter lofted into the stratosphere will circle the globe within weeks, forming a layer of aerosols that blocks incoming sunlight. The effect is similar to what occurs after a major volcanic eruption, but on a vastly larger scale. The eruption of Mount Tambora in Indonesia in 1815 ejected roughly 100 cubic kilometers of material into the atmosphere and caused the year without a summer in 1816, when crop failures and famine struck across Europe and North America. A 1-kilometer asteroid impact would inject far more material, potentially thousands of cubic kilometers, and the resulting cooling would be far more severe and far longer lasting. Climate models of post-impact scenarios, developed by researchers at institutions including NASA's Goddard Institute for Space Studies, the National Center for Atmospheric Research, and multiple European universities, consistently show global temperature drops of 5 to 15 degrees Celsius lasting for years following a 1-kilometer impact. In the temperate regions of the Northern Hemisphere, where the majority of the world's agriculture takes place, these temperature drops would be catastrophic. Growing seasons would shrink or vanish entirely. Staple crops, wheat, rice, corn, soybeans, would fail across entire continents. The global food supply, already strained by population growth and climate change, would collapse, and the agricultural failure would cascade. Modern civilization is not a collection of independent, self-sufficient communities. It is a single, tightly integrated global system. Food production depends on fuel, which depends on refineries, which depend on electricity, which depends on supply chains that span continents. A disruption severe enough to collapse agriculture would also collapse the systems that agriculture depends on, creating a feedback loop of failure that would propagate through every sector of the global economy simultaneously. The word civilization implies a level of coordination and complexity that is both humanity's greatest strength and its greatest vulnerability. The more complex the system, the more catastrophically it fails when the foundation is pulled away. Beyond the dust and the cold, there are additional effects that compound the disaster. The energy of the impact would heat atmospheric nitrogen and oxygen to temperatures high enough to form nitrogen oxides, compounds that destroy ozone. The resulting damage to the ozone layer would allow increased ultraviolet radiation to reach the surface, harming surviving vegetation and exposed organisms. The nitrogen oxides would also combine with water to form nitric acid, producing acid rain that would further damage ecosystems and contaminate freshwater supplies. And if the impact strikes a carbonate-rich region, the thermal decomposition of carbonate rock would release enormous quantities of carbon dioxide, potentially triggering long-term greenhouse warming after the initial cooling phase subsides, a cruel double punch of ice followed by fire. The sum of these effects, the darkness, the cold, the crop failure, the ozone depletion, the acid rain, the infrastructure collapse, is what planetary scientists mean when they use the term global catastrophe. It does not mean that everyone dies. It means that the organized systems on which billions of people depend for food, water, shelter, medical care, and social order cease to function. The survivors, and there would be survivors, would face a world that has been set back by centuries in its capacity to sustain large populations. The recovery, if it occurs, would take generations. This is the stakes against which the planetary defense challenge must be measured. Not the probability of impact, which is low, not the timeline, which is long, but the magnitude of the consequence, which is total. And when the consequence is total, even a low probability demands serious attention. There is a concept in risk analysis called expected loss, calculated as the probability of an event multiplied by the cost of the event. For 1950 DA, the probability is roughly 1 in 8,300. The cost, if we attempt to quantify it in economic terms, which is itself an inadequate measure but useful for comparison, would be in the hundreds of trillions of dollars, encompassing the destruction of global infrastructure, the loss of agricultural capacity, and the death of billions of people. The expected loss, even at a probability of 1 in 8,300, is therefore in the tens of billions of dollars. That is the rational investment threshold, the amount a purely rational actor would be willing to spend to prevent the event, and it is orders of magnitude more than what is currently being spent on planetary defense worldwide. The disparity between the rational investment and the actual investment is one of the most striking features of the 1950 DA story. It reveals, more clearly than perhaps any other example, the gap between how humanity should allocate resources and how it actually does. We spend hundreds of billions of dollars per year on military defense against human adversaries, whose capacity for destruction, while real, is dwarfed by the potential of a single asteroid. We spend trillions on economic systems designed to optimize short-term returns at the expense of long-term resilience. And we spend almost nothing on the one threat that could end the game entirely. But the challenge of deflection is not merely a matter of choosing the right technology. It is also a matter of choosing the right time to act. And that decision depends on resolving a paradox that sits at the very heart of the 1950 DA problem. The paradox is this: the optimal time to deflect an asteroid is as far in advance of the impact as possible. With 850 years of lead time, the required velocity change to miss Earth is vanishingly small, perhaps a fraction of a millimeter per second. A single well-aimed kinetic impactor might suffice. With 50 years of lead time, the required change jumps by orders of magnitude, and the mission becomes enormously more complex and expensive. With 5 years of lead time, deflection of a 1-kilometer object is effectively impossible with any technology we can foresee. But here is the paradox. The further in advance you try to deflect, the less certain you are that deflection is necessary. The orbital prediction for 1950 DA in 2880 has a range of uncertainty so large that it encompasses both a hit and a clean miss by millions of kilometers. Acting now, while the required force is smallest, means acting on a probability, not a certainty. And acting on a probability means accepting the possibility that the entire effort was unnecessary, that the asteroid would have missed anyway, that the billions of dollars and decades of effort were wasted on a phantom threat. No political leader wants to be remembered for spending a nation's treasure fighting a ghost. And no political leader wants to be remembered for ignoring a warning that turned out to be real. The paradox of planetary defense is that both outcomes are possible, and the decision cannot be deferred until the answer is known, because by then it may be too late. The academic literature on this problem is extensive and sobering. Decision theorists, risk analysts, and aerospace engineers have published dozens of papers exploring the question of when to act, how much to spend, and how to balance the costs of unnecessary action against the costs of delayed action. The consensus, insofar as one exists, is that the optimal strategy is staged investment. Begin with characterization, then technology development, then precursor missions, then, if the probability warrants it, deflection. Each stage provides information that informs the decision to proceed to the next. Each stage is relatively inexpensive compared to the final deflection mission, and each stage reduces the uncertainty, narrowing the range of possible outcomes and bringing the decision point into sharper focus. This staged approach is rational, it is proportionate, it is defensible, and it is not happening. As of the mid-2020s, no characterization mission to 1950 DA has been approved. No technology development program specifically targeting 1-kilometer asteroid deflection has been funded. No staged investment plan has been adopted by any space agency or international body. The strategy exists on paper. The implementation exists nowhere. The reason is the same reason that has recurred throughout this story. The timescale is too long. The probability is too low. The cost is too high relative to the perceived benefit. And the political system, optimized for 4-year electoral cycles, cannot process a threat that operates on an 850-year timeline. The staged approach requires the first investment to be made now, and now is the one thing that the political system cannot commit to for a problem that will not arrive for centuries. There is an old proverb that says the best time to plant a tree was 20 years ago, and the second best time is now. For 1950 DA, the best time to begin preparations was when the threat was first identified in 2002. 20 years have already passed. The second best time is now. The third best time will be tomorrow. And the worst possible time is later, because later has a way of becoming too late. The story of humanity's attempts to prepare for threats like 1950 DA is not a single narrative. It is a series of chapters, each one driven by different people, different technologies, and different ideas about what it means to protect a planet. Some of those chapters ended in triumph. Others ended in frustration. And taken together, they reveal both the extraordinary ingenuity of our species and the stubborn limits of our reach. The first chapter begins, not with 1950 D at all, but with a realization that came slowly and painfully to the scientific community over the second half of the 20th century. The realization that impacts are not ancient history. They are ongoing, and they can happen to us. For most of human history, rocks falling from the sky were dismissed as folklore. In 1794, when a meteorite shower fell near the town of Siena, Italy, and was witnessed by hundreds of people, the leading scientists of the day refused to believe it. The great French chemist Antoine Lavoisier reportedly declared that stones could not fall from the sky because there were no stones in the sky. It was a statement of logical elegance and absolute wrongness. It took another decade, and the fall of a massive meteorite shower near L'Aigle, France, in 1803, before the French Academy of Sciences formally acknowledged that, yes, rocks do fall from space. Even then, the implications were slow to sink in. If small rocks fall, could large ones fall too? And if large ones fall, what would that mean for life on Earth? The answer came in pieces. In 1906, Daniel Barringer, a mining engineer from Philadelphia, arrived at a bowl-shaped depression in the Arizona desert and declared it was an impact crater formed by a massive iron meteorite. The scientific establishment disagreed. For decades, the prevailing view was that the crater, now called Barringer crater or meteor crater, was volcanic in origin. Barringer spent 25 years and most of his personal fortune trying to find the buried meteorite, drilling into the crater floor, hiring geologists, publishing papers. He never found the main mass because, as we now understand, most of it was vaporized on impact. Barringer died in 1929, exhausted and financially ruined, still fighting for recognition. It was not until the 1960s when Eugene Shoemaker identified coesite and stishovite, high-pressure forms of quartz that can only form under the extreme conditions of a hypervelocity impact, that the crater's origin was conclusively established. Barringer was right, the establishment was wrong, and the implications were enormous. Shoemaker did not stop there. Having proven that Barringer crater was an impact structure, he turned his attention to the broader question: how common are impacts, and how dangerous are they? He became one of the first scientists to systematically study the near-Earth asteroid population, to estimate impact rates, and to argue publicly that a large impact was not a matter of if, but when. He lobbied for survey programs. He spoke at congressional hearings. He wrote papers with titles that were designed to alarm, and he was largely ignored. Through the 1970s and 80s, asteroid impact remained a fringe concern, overshadowed by the Cold War, the space race, and the more immediate terrors of nuclear annihilation. Then came Shoemaker-Levy 9. In March 1993, astronomers Carolyn Shoemaker, Eugene Shoemaker, and David Levy discovered a comet near Jupiter that was unlike anything anyone had seen before. The comet had been captured by Jupiter's gravity and torn apart by tidal forces into a string of fragments, a celestial train of icy debris stretching across millions of kilometers. Orbital calculations showed that these fragments were on a collision course with Jupiter, set to impact the giant planet in July 1994. For the first time in human history, scientists knew in advance that a cosmic impact was about to occur, and they could watch it happen. The impacts began on July 16, 1994, and continued for 6 days. Fragment after fragment slammed into Jupiter's atmosphere at roughly 60 kilometers per second. The largest fragments, estimated at 1 to 2 kilometers in diameter, exploded with energies of hundreds of thousands of megatons. The resulting fireballs rose above Jupiter's limb, visible in telescopes on Earth. Dark scars, each one larger than the Earth itself, appeared in Jupiter's banded atmosphere and persisted for months. The images were broadcast worldwide. For the first time, the abstract concept of a cosmic impact became visceral, visual, undeniable. This was not a theoretical calculation. It was a real event, observed in real time, producing real devastation on a scale that beggared imagination. The psychological impact on the scientific community and on policymakers was profound. In the aftermath of Shoemaker-Levy 9, The United States Congress directed NASA to identify and catalogue at least 90% of near-Earth objects larger than 1 kilometre within 10 years. The SpaceGuard survey, as it was called, launched in 1998 and eventually exceeded its goal. By the early 2010s, NASA estimated that more than 90% of near-Earth asteroids larger than 1 kilometre had been discovered. The vast majority posed no threat, but the survey also revealed how many objects were out there, how many orbits crossed Earth's path, and how much remained unseen in the smaller size ranges. And among the objects found in that era of accelerated discovery was the rediscovered 1950 DA. The second chapter of this story is about characterization, the painstaking effort to understand what an asteroid actually is. Not just where it is going, but what it is made of, how it is put together, and how it would respond to a deflection attempt. Because, as the planetary defense community quickly realized, knowing that an asteroid exists and knowing how to move it are two very different problems. The radar observations of 1950 DA in 2001 were the first major step. As described earlier, they revealed the asteroid's size, shape, and extraordinarily fast rotation. But radar from Earth can only tell you so much. It gives you the outline, it gives you the spin, it gives you a rough estimate of surface roughness. What it cannot give you is the interior, and for deflection planning, the interior is everything. What is inside 1950 DA? Is it a homogeneous mass of rock? Is it a heterogeneous rubble pile with voids of varying size? Is there a dense core surrounded by a looser mantle? Are there regions of different composition? Perhaps a metallic inclusion embedded in a silicate matrix? The answers to these questions determine how the asteroid would respond to every proposed deflection method. And as of the mid-2020s, we do not have those answers. The challenge of characterizing asteroid interiors has driven some of the most creative mission concepts in the history of space exploration. One approach, proposed in multiple forms since the early 2000s, is to send a spacecraft to orbit the asteroid and use radio science, the precise measurement of the spacecraft's trajectory as it orbits, to map the asteroid's internal mass distribution. Variations in the gravitational field caused by variations in internal density would cause the spacecraft's orbit to deviate in measurable ways. From those deviations, scientists could build a three-dimensional model of the interior. This technique has been successfully applied to other bodies. NASA's Grail mission, which orbited the Moon in 2011 and 2012, used two spacecraft flying in formation to map the lunar gravitational field with extraordinary precision, revealing the structure of the crust, the distribution of subsurface magma deposits, and the signatures of ancient impacts. A similar mission to 1950 DA could, in principle, provide the interior model needed for deflection planning, but no such mission has been proposed, funded, or launched. The asteroid is not scheduled for a close approach favourable for radar observation until later in the 21st century, and the political appetite for a precursor mission to an asteroid that might not hit Earth for 850 years is, to put it gently, limited. Another approach to understanding asteroid interiors comes from laboratory experiments. Researchers at universities in the United States, Japan, and Europe have spent decades studying the physical properties of simulated asteroid material, mixtures of crushed rock, fine dust, and vacuum-compatible analogues designed to mimic the conditions on and inside a rubble pile asteroid. These experiments have revealed that very fine-grained material, particles smaller than a few tens of micrometers, can exhibit significant cohesive strength due to van der Waals forces, the same intermolecular attractions that allow geckos to climb glass. The cohesive strength measured in these experiments is small by every standards, on the order of a few hundred pascals, roughly the pressure exerted by a single sheet of paper lying on a table. But for an asteroid in microgravity, where the gravitational compressive forces are already minuscule, even this tiny cohesion can be decisive. It can mean the difference between a rubble pile that obeys the spin barrier and one that exceeds it. These laboratory results have been used to build theoretical models of 1950 DA's interior. In 2014, a team led by Ben Rosaitis at the Open University in the United Kingdom published a paper in the journal Nature that examined the spin state of 1950 DA in detail. Their analysis showed that the asteroid's density and spin rate were inconsistent with a body held together by gravity alone. Some form of cohesive strength was required, and the required strength was within the range measured in laboratory experiments. The conclusion was striking. 1950 DA is likely a rubble pile held together by van der Waals forces between its constituent grains. It is, in a sense, a giant sandcastle in space, bonded not by moisture but by the feeble electromagnetic attraction between dust particles. A sandcastle, a 1.1-kilometer sandcastle, spinning at the edge of self-destruction, containing the potential energy to end a civilization. Let that sink in. The third chapter of this story takes us to what has arguably been the most significant practical step in planetary defense to date. NASA's DART mission, the Double Asteroid Redirection Test. DART was not designed for 1950 DA specifically. It was designed as a proof of concept, a demonstration that a kinetic impactor could measurably change an asteroid's orbit. But its results have profound implications for the 1950 DA problem, both encouraging and sobering. The target was Dimorphos, a small moonlet orbiting a larger near-Earth asteroid called Didymos. Dimorphos is roughly 160 meters across, roughly the size of a football stadium, orbiting Didymos at a distance of about 1.2 kilometers, with a period of approximately 11 hours and 55 minutes. The DART spacecraft, a box-shaped probe about the size of a vending machine, with two large solar arrays, was launched from Vandenberg Space Force Base in California on November 24, 2021, aboard a SpaceX Falcon 9 rocket. After 10 months of cruise through interplanetary space, DART arrived at the Didymos system on September 26, 2022. The approach was autonomous. In the final hours, the spacecraft's onboard camera, called Duraco, detected the Didymos system as a pair of bright dots against the star field. As the spacecraft closed in, the dots resolved into shapes. Didymos, the larger body, filled the frame first, a rough, diamond-shaped rock strewn with boulders. Then Dimorphos appeared, smaller, rounder, a pile of rubble and rocks with no single dominant feature. The spacecraft locked onto Dimorphos and fired its thrusters for the final approach, navigating autonomously with no possibility of human intervention. The light time delay between Earth and the spacecraft was roughly 45 seconds. By the time mission controllers saw anything, the impact had already happened. At 7:14 in the evening, Eastern Daylight Time, the DART spacecraft struck Dimorphos at a relative velocity of approximately 6.1 kilometers per second. The impact was observed by a companion spacecraft called LYSIACube, provided by the Italian Space Agency, which had separated from DART 2 weeks earlier and was trailing behind at a safe distance. LYSIACube's cameras captured the moment of impact and the aftermath. A brilliant flash, followed by an expanding cone of debris, fragments of rock and dust launched from the surface of Dimorphos by the tremendous energy of the collision. The plume of ejected material extended thousands of kilometers from the asteroid, a visible scar in space, captured by telescopes on Earth, by the Hubble Space Telescope, and by the James Webb Space Telescope. The result exceeded expectations. Subsequent observations by ground-based telescopes showed that Dimorphos's orbital period around Didymos had changed by approximately 32 minutes, from roughly 11 hours and 55 minutes to roughly 11 hours and 23 minutes. The change was far greater than the minimum success threshold of 73 seconds that mission planners had set. The reason for the larger-than-expected change was the ejected debris itself. When DART struck Dimorphos, it did not just push the asteroid with its own momentum. It blasted a massive amount of surface material off the asteroid, and that material, flying away in the opposite direction, acted like rocket exhaust, adding to the push. The momentum enhancement factor, the ratio of total momentum delivered to the asteroid relative to the momentum of the spacecraft alone, was estimated at between 3 and 4. In other words, the ejected material roughly tripled the effectiveness of the impact. This was excellent news for planetary defense, with one enormous caveat. Dimorphos is a rubble pile, and it responded to the impact by excavating and ejecting a tremendous amount of material. That ejection amplified the deflection, but the response of a different rubble pile, with different grain sizes, different cohesion, different internal structure, might be very different. An asteroid with a thick layer of fine regolith might absorb the impact energy without ejecting as much material, reducing the momentum enhancement factor. An asteroid with significant internal voids might transmit the shock wave unevenly, producing a chaotic, unpredictable response. An asteroid spinning near its breakup speed, like 1950 DA, might respond to a kinetic impact by fragmenting entirely, with some fragments continuing on the original collision course and others scattering in unpredictable directions. The DART team was careful to emphasize these uncertainties. Andy Rivkin, the DART investigation team lead at the Johns Hopkins Applied Physics Laboratory, noted that DART tested one scenario on one target, and that extrapolating to other asteroids required caution. Nancy Chabot, the DART coordination lead, put it more bluntly. Each asteroid is different, she said. You would want to characterize the target before you tried to deflect it. That single sentence captures one of the deepest challenges facing the planetary defense of 1950 DE. You would want to characterize the target. But we have not characterized it. We have radar data from 2001. We have estimates of its size, shape, spin, and approximate density. We have theoretical models of its possible internal structure. But we have not visited it. We have not orbited it. We have not landed on it. We have not taken a sample of its surface. We do not know what it looks like up close. We do not know if its surface is covered in fine regolith or blocky boulders or exposed bedrock. We do not know the composition of its interior. We do not know whether the cohesive forces that hold it together are uniform or concentrated. We do not know any of the things we would need to know to plan a deflection mission with confidence. The fourth chapter in this story is about an idea that sounds like science fiction, but may be the most practical long-term approach to the 1950 DA problem. The concept of a dedicated rendezvous mission, a spacecraft sent not to deflect the asteroid, but simply to study it, to orbit it for months or years, to map every boulder, measure every gravitational anomaly, sample every surface feature, and return to Earth with the data needed to plan a real deflection, a precursor mission in the jargon of planetary defense, a reconnaissance flight. Several precursor mission concepts have been studied. In the early 2000s, researchers at NASA's Jet Propulsion Laboratory explored the idea of sending a small spacecraft to rendezvous with 1950 DA during one of its close approaches to Earth, entering orbit around the asteroid and using a combination of cameras, spectrometers, radar-sounding instruments, and radio science to characterize the body from the outside in. The estimated cost was in the range of $500 million to $1 billion, comparable to a mid-range planetary science mission. The technical challenges were significant, but not beyond existing capability. The mission would need to navigate to a 1-kilometer object in deep space, enter orbit around a body with an extremely weak and irregular gravitational field, and operate autonomously for months while in close proximity to a rapidly spinning, irregularly shaped target. But navigating to the asteroid is only half the challenge. The other half is timing. 1950 DA is in an orbit that brings it close to Earth only periodically, and the windows for launch and rendezvous are constrained by the relative positions of Earth and the asteroid. The optimal launch windows are separated by years or decades, and missing one means waiting for the next. As of the mid-2020s, no precursor mission to 1950 DA has been formally proposed to any space agency. No funding has been allocated and no timeline has been established. The asteroid remains, in the language of the planetary defense community, a characterization gap, a known threat about which we know too little. And this brings us to the fifth and perhaps most unsettling chapter of this story. The chapter about what happens when a civilization knows about a threat, but cannot agree on what to do about it, when the science is clear, but the institutions are inadequate, when the engineering is possible, but the politics are impossible. In 2013, the United Nations General Assembly established the International Asteroid Warning Network, IORN, and the Space Mission Planning Advisory Group, SMPAG, two bodies tasked with coordinating the international response to potentially hazardous asteroids. IORN is responsible for detecting, tracking, and characterizing near-Earth objects. SMPAG is responsible for planning deflection missions. Together, they represent the closest thing humanity has to a global planetary defense infrastructure. But their powers are advisory. They can recommend. They cannot fund. They cannot build. They cannot launch. The actual capability to mount a deflection mission rests with individual space agencies, primarily NASA, the European Space Agency, and an increasingly capable Chinese space program. And those agencies are funded by national governments, which are accountable to voters, who care about the next election, not the next millennium. The disconnect between the threat and the response is not a failure of science. It is a failure of governance. The planetary defense community has done its job. The asteroids have been found. The risks have been quantified. The technologies have been demonstrated, at least at small scale. The precursor mission concepts have been designed. The deflection strategies have been analyzed. The scientific foundation is solid. What is missing is the bridge between knowledge and action, the institutional mechanism that converts scientific understanding into funded programs with specific timelines and measurable milestones. And for 1950 DA specifically, the challenge is compounded by the timescale. A precursor mission to characterize the asteroid would take 5 to 10 years to plan, build, and launch, and perhaps another 5 years to reach the target and complete its observations. The resulting data would then need to be analyzed, the deflection strategy selected, the deflection mission designed, tested, and launched. The total timeline from decision to deflection could easily span 30 to 50 years. That is well within human capability. But the decision itself might not come for centuries, because the probability of impact is not yet high enough to justify the cost, and the political system is not designed to spend money preventing events that might not happen for 8 centuries. The math is striking when you lay it all out. The cost of a precursor mission is perhaps $1 billion. The cost of a deflection mission might be $10 to $50 billion. The cost of doing nothing, if the asteroid hits, is the end of civilization. A rational species would spend the $1 billion on characterization without hesitation. A rational species would begin deflection preparations well in advance, scaling up as the probability became clearer. A rational species would treat an 850-year warning as a gift, not a burden. But rationality, in the collective sense, is not a feature of human governance. It is an aspiration, frequently overwhelmed by shorter-term pressures, partisan calculations, and the fundamental inability of democratic systems to bind future generations to present commitments. This is not a condemnation of democracy. It is a recognition of its limits. The same political system that produces accountability, responsiveness, and individual rights also produces short-sightedness, inconsistency, and an allergy to long-term investment. And planetary defense is nothing if not a long-term investment. So where does that leave us? It leaves us with an asteroid that we have identified but not characterized, a threat that we have quantified but not resolved, a set of deflection technologies that have been demonstrated in miniature but never tested at scale, a political system that is structurally incapable of sustained multi-century planning, and a probability of impact that is high enough to be the worst on record but low enough to be ignored. The chapters of this story do not end with a resolution. They end with an ellipsis. Each attempt to address the problem, from Shoemaker's early warnings to the SpaceGuard survey to DART to the UN working groups, has been a genuine step forward. But each step has also revealed how much further we have to go. And the clock, silent and indifferent, continues to tick. There is a 6th chapter to this story, one that is still being written, and it concerns the newest frontier of planetary defense research, the use of artificial intelligence, autonomous systems, and advanced propulsion to close the gap between what we can do now and what we will need to do if 1950 DA proves to be on a collision course. At the Johns Hopkins Applied Physics Laboratory, the same institution that built and operated the DART spacecraft, engineers have begun studying next-generation deflection concepts that go far beyond the simple kinetic impactor. One concept, known as the enhanced kinetic impactor, involves launching a spacecraft that arrives at the asteroid months or years before the main impactor. This scout spacecraft would orbit the asteroid map its surface in detail, measure its mass and gravity field, and identify the optimal impact point, the location where a kinetic strike would deliver the maximum momentum transfer with the minimum risk of fragmentation. The Scout would then relay this targeting data to the main impactor, which would use onboard autonomous navigation to steer itself to the designated point with meter-level precision. The combined system would be far more effective than a blind impact, turning the kinetic impactor from a blunt instrument into a precision tool. Another concept under study is the ion beam deflection approach, in which a spacecraft equipped with a powerful ion thruster stations itself near the asteroid and directs its exhaust plume at the surface. The ions, accelerated to tens of kilometers per second by the electric field of the thruster, bombard the asteroid's surface and erode it, gradually transferring momentum to the asteroid through the continuous stream of high-energy particles. The advantage of this approach is that it does not require contact with the surface and does not risk fragmentation. The disadvantage is that it is slow. An ion beam deflection system operating at the power levels achievable with current solar electric propulsion technology would need years or decades to accumulate a meaningful velocity change on a 1-kilometer asteroid, but with sufficient lead time, which is precisely what 1950 DA offers, it could be effective. Then there is the concept of the laser ablation system, perhaps the most futuristic of the proposals currently under study. In this approach, a spacecraft carrying a high-power laser is stationed near the asteroid. The laser beam is focused on the surface, heating a small spot to temperatures high enough to vaporize the rock. The expanding plume of vaporized material generates thrust, slowly pushing the asteroid off course. The advantage is precision. The laser can be aimed at specific points on the surface, and the thrust can be modulated by adjusting the beam power. The disadvantage is the enormous power requirement. A laser system capable of vaporizing rock at useful rates would need tens or hundreds of kilowatts of continuous power, far beyond what current spacecraft solar arrays can provide. Future developments in space-based nuclear power or ultra-efficient solar arrays might close this gap, but those developments are themselves decades away. Each of these concepts, the enhanced kinetic impactor, the ion beam deflector, the laser ablation system, represents a genuine advance over the crude throw-a-rock at a rock approach of DART. Each addresses specific limitations of the kinetic impactor, and each would benefit enormously from the long lead time that 1950 DA provides. With 850 years, even the slowest of these methods becomes viable. The question is not whether they can work in principle. The question is whether they will be developed, tested, and deployed in practice. And here the story circles back to the fundamental tension that runs through every chapter, the tension between capability and will, between what we can do and what we choose to do. The technologies are real, the physics is sound, the engineering is challenging but achievable. What is missing is the sustained commitment to turn concepts into hardware, hardware into missions, and missions into operational capability. And that commitment, as we have seen, depends on factors that lie outside the domain of science and engineering: political leadership, public awareness, institutional persistence, and the willingness to invest in a future that none of us will live to see. There is one more aspect of the 1950 DA challenge that rarely receives attention but may ultimately prove decisive: the question of international cooperation. Deflecting a 1-kilometer asteroid is not a project that any single nation can accomplish alone. The scale of the required effort, the diversity of the technologies involved, the duration of the program, and the global nature of the threat all demand a level of international collaboration that has few precedents in human history. The International Space Station, built and operated by 5 space agencies across 15 nations, is perhaps the closest analogue, but the ISS program spans decades, not centuries, and its budget, while large, is a fraction of what a full-scale deflection program would require. The geopolitical challenges are formidable. Planetary defense involves dual-use technologies, systems that could be used for deflection but also for weaponization. A kinetic impactor capable of deflecting an asteroid is also, in principle, capable of being redirected toward a target on Earth. a nuclear standoff detonation device designed for asteroid deflection, is also a nuclear weapon in space. The political sensitivities around these technologies are intense, and they are compounded by the current state of international relations, which is characterized by rivalry, mistrust, and a retreat from the multilateral institutions that were established after the Second World War. And yet, planetary defense is one of the few areas where international cooperation is not just beneficial but essential. An asteroid impact does not respect national borders. Its consequences are global. A deflection mission launched by one nation protects all nations. The incentive structure, in economic terms, is that of a pure public good. Everyone benefits, whether or not they contribute. This creates the classic free rider problem. Each nation has an incentive to let others bear the cost, while enjoying the protection. The result, predictably, is underinvestment by all. Breaking this cycle would require a new kind of international agreement, something more binding than the current advisory structures, and more focused than the existing space treaties. It would require shared funding mechanisms, joint mission planning, agreed protocols for decision-making, and a governance structure capable of sustaining a program across centuries. Nothing like this has ever existed. But then, nothing like 1950 DA has ever been discovered before, and there is one final dimension of the 1950 DA challenge that connects it to the broadest questions of human existence, the question of what kind of species we want to be. We stand at a peculiar moment in the history of life. For the first time, a species has developed both the knowledge to foresee existential threats and the technology to potentially prevent them. This is a new capability in the 4 billion-year story of life on Earth. It has never existed before. No previous dominant species, not the trilobites, not the dinosaurs, not the great marine reptiles of the Mesozoic, had any ability to detect, predict, or prevent a catastrophic impact. They lived and died at the mercy of orbital mechanics. We do not have to. But having the capability is not the same as using it. A gun in a holster is not the same as a gun in the hand. A fire extinguisher on the wall is not the same as one being aimed at a blaze. The capability is potential, the use is actual, and the gap between the two, for 1950 DA, remains vast. Scientists at NASA's Center for Near-Earth Object Studies have been careful to frame the 1950 DA challenge not as an immediate emergency, but as a long-term planning problem. The language is measured, the tone is calm, the message is consistent. We have time, but we should not waste it. They speak of knowledge gaps and observation campaigns and technology readiness levels. They do not speak of doom or panic or urgency. And that restraint is appropriate, because panic would be counterproductive and inaccurate. The probability of impact is low. The timeline is long. There is no cause for alarm in the conventional sense. But there is cause for action. There is cause for sustained, methodical, well-funded preparation. There is cause for the kind of quiet, unglamorous, long-term thinking that does not make headlines but makes civilizations resilient. And the only question that ultimately matters, is whether we will provide that cause with the resources and the institutional continuity it requires. The story of how humanity has responded to past impact threats offers both hope and warning. When Apophis was identified as a potential threat in 2004, the response was swift and effective. Additional observations were collected rapidly. The orbital uncertainty was reduced. The threat was resolved within a few years. The system worked because the timescale was short and the probability was initially high. Two conditions that align perfectly with human cognitive and institutional capabilities. When the Chelyabinsk event occurred in 2013, the response was similarly swift. Within hours, the scientific community had identified the object as a small near-Earth asteroid. Within days, the trajectory and energy had been estimated. Within months, the event had been analyzed in detail and published in peer-reviewed journals. Within years, it had become a benchmark event in planetary defense research, a natural experiment that validated impact models and highlighted the need for better detection of small, sun-approaching objects. These successes demonstrate that humanity can respond to impact threats effectively when the timeline is compressed and the evidence is immediate. The challenge of 1950 DA is that neither condition applies. The timeline is measured in centuries, not years. The evidence is probabilistic, not definitive. And the response, if it comes, will need to be sustained across a span of time that dwarfs every program humanity has ever undertaken. Whether we rise to that challenge will determine not just the fate of a single asteroid, but the trajectory of our species. If we can learn to think in centuries, to plan beyond our lifetimes, to invest in a future we will never see, then we will have crossed a threshold that separates a young, reactive civilization from a mature, proactive one. And if we cannot, if the rock arrives and finds us unprepared, then the universe will have delivered its lesson in the most unforgiving way possible. Not through malice, but through indifference, the same indifference that governs the fall of every rock, the death of every star, and the silence between the galaxies. There is a deeper truth hidden inside the story of 1950 DA, a truth that has nothing to do with orbital mechanics or deflection technology or the probability of impact. It is a truth about what it means to be a species that can see the future but cannot act on what it sees. A truth about the strange, painful gap between knowledge and response, between understanding and will, between the mind that comprehends a danger and the civilization that fails to address it. We live on a planet that has been struck by large objects from space repeatedly across its 4.6 billion year history. We know this. The evidence is written in the rock, in the craters, in the fossil record of mass extinctions. We know that the process is ongoing, that the solar system is full of debris, and that near-Earth objects cross our path regularly. We have built telescopes to find these objects, and we have found them by the tens of thousands. We have developed theoretical frameworks for deflecting them. We have even tested one method successfully on a small target. We have done, in many ways, exactly what a thoughtful, prudent civilization should do. And yet, when you look at the actual state of readiness, at the distance between what we know and what we have done, between the threat and the response, you see something disquieting. We have identified 34,000 near-Earth objects, but we have characterized the interiors of almost none of them. We have tested a kinetic impactor on a 160-meter rubble pile, but we have no tested method for deflecting a 1-kilometer object. We have international advisory bodies for planetary defense, but they have no authority and almost no funding. We have a list of potentially hazardous asteroids, and 9050 DA sits on that list, flagged as the most threatening known object for a specific future date, and no mission to visit it is planned, funded, or even formally proposed. Let that sink in. The single most threatening known asteroid in the solar system, an object with a non-zero probability of ending civilization on a specific date, and we have not sent a spacecraft to look at it. We have not measured its surface composition. We have not mapped its gravitational field. We have not determined whether it is a solid monolith or a fragile sandcastle. We do not know the one thing we most need to know, how it would respond to a deflection attempt, and we are not, as of the mid-2020s, making any plans to find out. This is not a failure of science. The scientists have done their part. They have found the asteroid, calculated the risk, published the papers, sounded the alarm. This is a failure of civilization, a failure of the collective mechanism by which a species converts knowledge into action, understanding into preparation, foresight into survival. And the failure is not unique to 1950 DA. It is a pattern that recurs across every long-term threat humanity faces. Climate change, antibiotic resistance, nuclear proliferation, pandemic preparedness. In each case, the science is clear, the warnings are issued, and the response is delayed, inadequate, or absent because the threat is too slow, too diffuse, too abstract, too far away to trigger the alarm systems that evolution built into our brains. We are wired for tigers, not for asteroids. We respond to the visible, the immediate, the personal. A rock that might hit in 850 years does not register on the same scale as a predator in the grass. There is a concept in cognitive psychology called temporal discounting, the tendency to value future rewards and costs less than present ones. It is one of the most robust findings in behavioral sciences. Given a choice between $100 today and $110 tomorrow, most people take the money now. Given a choice between preventing a catastrophe in 10 years and preventing one in 850 years, most people, most governments, most civilizations will focus on the near-term threat and defer the distant one. This is not irrational in the narrow sense. In a world of limited resources and uncertain information, prioritizing immediate threats over distant ones is often the best strategy. But when the distant threat is existential, when the cost of delay may be total and irreversible, temporal discounting becomes a trap. It is a cognitive shortcut that works perfectly well for everyday decisions and catastrophically for civilizational ones. 1950 DA exposes this trap with merciless clarity. The asteroid provides the longest warning time in the history of threat assessment, 850 years. That is longer than the entire history of the Ottoman Empire, longer than the time between the fall of Constantinople and the present day, longer than the English language has existed in anything close to its modern form. By any measure, it is an extraordinary gift of time. And the question that haunts every planetary defense scientist who has studied this problem is whether that gift will be used or wasted. The honest answer, based on everything we know about human behavior and institutional persistence, is that it will probably be wasted. Not entirely. Small steps will be taken. Papers will be published. Conferences will be held. Perhaps eventually a precursor mission will be launched. The data will come in. The models will improve. The probability will be revised, up or down. But the decisive action, the commitment to a multi-decade deflection campaign, will almost certainly be deferred, again and again, generation after generation, until the probability becomes high enough to override the political inertia. And by then, the window for gentle deflection may have closed. This is not science fiction. This is the baseline prediction of nearly every long-term planning analysis that has been applied to the 1950 DDA problem. Not because the analysts are pessimistic, but because the historical record offers no example of a civilization sustaining a focused, expensive, multi-century program against a threat that has not yet materialized. The Manhattan Project took 3 years, the Apollo program took 9. Even the most ambitious infrastructure projects, the great cathedrals of medieval Europe, took at most a few centuries, and they were sustained by religious motivation so powerful that it transcended individual lifetimes. Planetary defense offers no such motivation. It is a purely secular, purely rational endeavor, and rationality, in the long run, always loses to the urgent distractions of the present. But perhaps there is a different way to think about this. Perhaps the lesson of 1950 DA is not about the asteroid at all. Perhaps it is about us. Consider what it means that we found this object. A century ago, we did not have the technology to detect it. 2 centuries ago, we did not understand that impacts from space were even possible. 3 centuries ago, we did not know what asteroids were. The fact that we can identify a threat 850 years in advance, calculate its probability, model its consequences, and design potential solutions is a testament to the extraordinary power of human intelligence. No other species on this planet in the entire 4 billion year history of life has ever possessed this capability. We are the first, and if we fail to act on it, we may also be the last. Every atom in your body was forged inside a dying star. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was synthesized in the cores of massive stars that lived and died billions of years before the sun was born. When those stars exploded, they scattered their enriched material across space, and that material eventually coalesced into new stars, new planets, and, on at least one small rocky world orbiting an unremarkable yellow dwarf, new life. You are, quite literally, the universe contemplating itself. And the universe, through you, has developed the ability to see a threat coming from 850 years away. Let that sink in. Not the threat, the capability. The sheer improbability that a thin film of biology on a small rock in the suburbs of an ordinary galaxy could develop radio telescopes, orbital mechanics, and radar astrometry precise enough to identify a specific object on a specific date nearly a millennium in the future. That is not a reason for despair. That is a reason for awe. And it is also a responsibility, because the capability to see a threat and the failure to respond to it is not just negligence. It is a betrayal of the very intelligence that made the detection possible. It is as if evolution spent 4 billion years building a brain capable of foresight, and the brain looked into the future, saw the danger, and went back to watching television. The deeper truth of 1950 DA is not that an asteroid might hit Earth. Asteroids have always hit Earth. The deeper truth is that for the first time in the history of life on this planet, a species exists that can do something about it. And the question is not whether the physics allows deflection. The physics does. The question is not whether the engineering is feasible. The engineering is given sufficient lead time and resources. The question is whether the species that develop the capability to see the threat will develop the wisdom to act on it. And that question remains unanswered. There is another dimension to this story that rarely gets discussed, partly because it is uncomfortable, and partly because it touches on questions that science alone cannot answer. The dimension of moral obligation to the future. Do we owe anything to the people who will be alive in 2880? They do not exist yet. They have no voice. They cannot vote, protest, or lobby. They are, in every practical sense, powerless, and yet they may be the ones who face the consequences of our inaction. If we choose not to characterize 1950 DA, not to develop the deflection technology, not to build the institutional frameworks needed for multi-century planning, and the asteroid does hit, those future people will pay the price for our negligence. They will live or die in a world shaped by decisions we made or failed to make centuries before they were born. The philosopher Derek Parfit, in his work on the ethics of future generations, argued that we have moral obligations to people who do not yet exist, that the mere fact of their futurity does not diminish their moral status. A person who will live in 2880 has the same claim to a safe and habitable world as a person living today. Their suffering, if it occurs, is no less real for being distant in time, and our responsibility for preventing that suffering, if we have the knowledge and the means, is no less binding for being exercisable only through planning and commitment rather than immediate action. This is a radical claim, and it challenges the foundations of most political and economic systems, which are built on the assumption that the present generation's interests take priority. But it is also a claim that follows naturally from the basic moral intuition that causing preventable harm is wrong, regardless of when the harm occurs. If you knew that a bridge would collapse in 800 years, killing thousands, and you had the ability to reinforce it today at modest cost, would you be morally justified in walking away because the people at risk had not been born yet? Most people, when presented with the question in that form, say no. You would reinforce the bridge. The distance in time does not erase the obligation. 1950 DA is the bridge. The reinforcement is a characterization mission, a deflection technology development program, and an institutional framework for long-term planetary defense. The cost is measurable and finite. The potential consequence of inaction is immeasurable and permanent, and the decision is ours. But decisions are made by institutions, not by individuals, and institutions, as we have seen, are not designed for this kind of temporal reach. The challenge of 1950 DA is not just a scientific challenge, or an engineering challenge, or a political challenge. It is a civilizational challenge, a test of whether human civilization can evolve beyond the constraints of its own cognitive and institutional architecture to address a threat that operates on a time scale longer than any single human life, longer than any single government, longer than any single culture. We have never passed this test before. Every long-term challenge that humanity has faced, from climate change to nuclear proliferation, has been addressed late, inadequately, and only under the pressure of immediate crisis. The pattern is clear. The warning comes first, the delay follows, the crisis arrives, the response finally begins. And for many threats, this pattern, while costly, is survivable. The damage from delayed action is real but not total. For an asteroid impact, the pattern may not be survivable. There is no graceful degradation with a 1-kilometer impactor. There is no adaptation. There is no muddling through. There is before and there is after, and the transition between them is measured in hours, not decades. If the warning is heeded too late, if the deflection fails, if the preparations are insufficient, the cost is not a worse outcome. The cost is everything. This is not science fiction. This is the sober, evidence-based assessment of the planetary defense community, a community of scientists and engineers who have spent their careers thinking about exactly this problem, and their consensus, expressed in papers, reports and conference presentations, is clear. The time to begin preparing is now, not because the threat is imminent, but because the preparations take time, and the time is finite, and the consequences of failure are infinite. And yet, even within this sobering assessment, there are threads of hope. Not the easy hope of a quick technological fix, but the harder, more durable hope that comes from watching a species slowly, grudgingly, learn from its mistakes. Consider the trajectory of planetary defense over the past 3 decades. In 1990, the field barely existed. There were a handful of researchers, almost no funding, and widespread skepticism that asteroid impacts were a real threat. By 2000, SpaceGuard was underway, and the first systematic surveys were discovering hundreds of new near-Earth objects every year. By 2010, the catalogue exceeded 10,000 objects. By 2020, the first deflection test had been designed, funded, and launched. By 2022, DART had successfully altered an asteroid's orbit for the first time in human history. The progress is real, it is measurable, it is accelerating. In 2028, the European Space Agency's Hera mission arrived at the Didymos-Dimorphos system to conduct a detailed survey of the aftermath of DART's impact. Hera carried a suite of instruments designed to measure the mass of Dimorphos, the size and shape of the impact crater, the internal structure of the moonlet using radar sounding, and the properties of the ejected debris. The data from Hera will not directly address the 1950 DA problem, but it will provide something almost as valuable, a ground truth calibration of our models. For the first time, we will know how a rubble pile asteroid actually responds to a kinetic impact, not in simulation but in reality. And that knowledge, however partial, will inform every future deflection plan, including any plan for 1950 DA. There is also the matter of new detection and tracking technology. The Vera-C, Rubin Observatory in Chile, which began operations in the mid-2020s, is conducting the Legacy Survey of Space and Time, a 10-year program to photograph the entire visible sky every few nights. This survey will discover millions of new solar system objects, including thousands of previously unknown near-Earth asteroids. Among those discoveries may be objects on collision courses with Earth that we currently know nothing about. But the survey will also provide dramatically improved orbital data for known objects, including 1950 DA, potentially refining its long-term trajectory and narrowing the uncertainty that currently clouds the 2880 prediction. And further into the future, missions like the proposed NEO-Surveyor, a space-based infrared telescope designed to detect and characterize near-Earth objects from their thermal emission, could provide the data needed to measure the Yarkovsky effect on 1950 DA directly. By tracking the asteroid's position with infrared precision over a baseline of years or decades, scientists could measure the tiny thermal thrust that is currently the largest source of orbital uncertainty. That measurement alone could resolve the 2880 prediction, telling us definitively whether the asteroid will hit or miss. These are not fantasies. They are funded programs, designed missions, and tested technologies. They will not solve the 1950 DA problem by themselves, but they are the foundation on which a solution could be built if the will exists to build it. The question that lingers, the question that no telescope or spacecraft or computer model can answer, is whether a species that evolved to flee predators and gather berries can learn to think in centuries. Whether the same brain that produces Mozart and calculus and the general theory of relativity can also produce the institutional patience required to sustain a planetary defense program across 30 generations. Whether the creature that split the atom and walked on the moon can also look at a dot of light in the sky, a dot that is 850 years from causing harm, and say, "We will not wait. We will act now, not because we are afraid, but because we are wise." That is the question 1950 DA asks. Not of scientists, not of engineers, not of politicians, of us, of the species, of the civilization, of the idea that intelligence, once it emerges, can become durable enough to protect itself from the universe that created it? And as of tonight, we do not have an answer. But the question is being asked, and that in the long history of a species that spent most of its existence unaware that rocks could fall from the sky is itself a kind of progress, a kind of hope, the thinnest, most fragile kind, but perhaps enough. There is a particular kind of loneliness in understanding a truth that most people will never confront. The planetary defense scientists who study 1950 DA experience this loneliness daily. They go to conferences and present their findings. They publish papers in journals with small readerships. They brief congressional committees that are already distracted by the next crisis. They speak at public events to audiences that listen politely and then return to their lives unchanged. They know something that matters enormously, and the knowing changes nothing. This is not self-pity. These scientists are driven by curiosity and a sense of duty, not by a desire for recognition. But the gap between the significance of their work and the attention it receives is a quiet tragedy of the modern world. We live in a civilization that has achieved extraordinary things, splitting atoms, decoding genomes, connecting billions of minds through a global information network, and yet we cannot sustain attention on a threat that might end it all. The problem is not ignorance. The information is available, the papers are published, the data is open. The problem is relevance. In a world of infinite competing demands on human attention, a rock that might hit in 850 years simply cannot compete with the rent bill, the medical diagnosis, the election, the war, and yet the rock does not need our attention to continue on its path. That is the cruel asymmetry of the situation. Our inattention does not diminish the threat. It only diminishes our ability to respond. Consider what the world would look like if 1950 DA were confirmed to be on a collision course. Not a probability, a certainty. The response would be immediate, total, and unprecedented. Every space agency on Earth would redirect resources to the deflection effort. International rivalries would be set aside. Funding would flow without political debate. The best minds in physics, engineering, materials science, and mission design would be mobilized. The program would become the most important human endeavor since the dawn of civilization, surpassing in urgency and scale even the greatest wars and the most ambitious exploration programs. That response, in its scope and intensity, is the appropriate reaction to the potential end of civilization. And the fact that we are capable of it, that we can imagine it and plan for it, and if pressed, execute it, is itself a source of hope. We are not helpless. We are not incapable. We are merely unprovoked. The tiger has not yet appeared in the grass, and until it does, the village sleeps. But the universe has a way of waking villages, sometimes gently, with a warning tremor or a distant light in the sky, sometimes violently, with no warning at all. Chelyabinsk was a tremor, Tunguska was a louder tremor, Chicxulub was the earthquake, and 1950 DA, if it strikes, would be another earthquake, arriving at a time and place determined not by our readiness, but by the indifferent arithmetic of celestial mechanics. There is a thought that sometimes surfaces late at night, in the quiet hours when the mind is free to wander beyond the boundaries of the practical and the immediate. It is a thought about time, about what 850 years really means, not as a number, not as an abstraction, but as lived experience. 850 years ago, from the vantage point of the year 2026, the world was a different place. The year 1176. In Europe, the Crusades were raging. The Angevin Empire was near its peak. Saladin was consolidating power in the Middle East. China was ruled by the Southern Song dynasty, a civilization that had already invented gunpowder, the compass, and movable type. In the Americas, the great city of Cahokia, near present-day St. Louis, was in decline, its mounds slowly being reclaimed by grass and time. In sub-Saharan Africa, the Kingdom of Zimbabwe was beginning its rise. The Mongol Empire did not yet exist. The Renaissance was 3 centuries away. The Scientific Revolution was 5 centuries away. The Industrial Revolution was 6 centuries away. The Wright brothers were 7 centuries away. Every institution, every nation, every language, every technology that existed in 1176 has either been transformed beyond recognition or has ceased to exist entirely. The English spoken in 1176 is unintelligible to a modern English speaker. The political structures, the economic systems, the religious beliefs, the daily realities of life, all of it has changed so completely that a person transported from 1176 to the present would be unable to function in the modern world. Now project forward the same distance. 850 years from now, the year 2876. What will that world look like? What languages will be spoken? What nations will exist? What technologies will be available? The honest answer is, we have no idea. The rate of change in human civilization is accelerating, not slowing. The difference between 2026 and 2876 will likely be even greater than the difference between 1176 and 2026. The people who will face the 1950 DA encounter will be as alien to us as we would be to a medieval peasant. And yet, in one narrow but critical sense, we are connected to them. We share a planet, we share an orbit, we share a vulnerability to objects that cross that orbit, and we share a responsibility to address that vulnerability, not because we owe them a debt in any contractual sense, but because we are the first generation in the history of life that has the knowledge and the capability to do so. If we pass that responsibility to the next generation without acting, and they pass it to the next and the next, then the chain of deferral may eventually reach a generation that runs out of time. Stand back from the details for a moment. Step away from the orbital mechanics and the deflection strategies and the probability calculations. Look at the whole picture, because the story of 1950 DA is not really a story about an asteroid. It is a story about a species standing at a threshold it has never approached before, the threshold between being a passive passenger in a dangerous universe and becoming an active participant in its own survival. For 4 billion years, life on Earth has been at the mercy of the cosmos. Asteroid impacts have reshaped the biosphere again and again, wiping out entire branches of the evolutionary tree, opening ecological niches for new forms to fill, steering the course of life through a combination of blind luck and mechanical indifference. The dinosaurs did not see Chicxulub coming. They could not. They had no telescopes, no mathematics, no concept of orbital mechanics. They were simply there, going about the business of being dinosaurs, when a rock 10 kilometers wide ended their 160 million year reign in an afternoon. They had no chance, no warning, no choice. We are different. For the first time in the history of life on this planet, a species exists that can see the rocks coming, that can calculate their orbits, that can design machines to deflect them, that can, in principle, prevent the kind of catastrophe that has ended worlds before. The question of whether we will actually do so is not a scientific question. It is a question about the character of our civilization. And the answer matters not just for the specific case of 1950 DA, but for every challenge that requires long-term thinking, sustained investment, and the willingness to act on behalf of people who do not yet exist. Climate change, pandemic preparedness, nuclear disarmament, the preservation of biodiversity, the responsible development of artificial intelligence. Each of these challenges shares the same fundamental structure as the 1950 DA problem. A threat that is real but slow, a response that is technically feasible but politically difficult, and a timeline that extends beyond the horizon of human attention. If we can solve the planetary defense problem, if we can develop the institutions and the will to sustain a multi-century program of observation, characterization, and eventual deflection, then we will have demonstrated something profound, not just about our engineering capability, but about our capacity for foresight, about our ability to transcend the cognitive limitations that evolution gave us, and think on timescales that matter for civilization, not just for individual lives. And if we cannot, if we look at a 1-kilometer rock spinning impossibly fast through the darkness and shrug because it is too far away to worry about, then we will have demonstrated something equally profound but far less flattering. That intelligence alone is not enough. That awareness without action is just a more sophisticated form of helplessness. That knowing the danger and failing to act is, in some ways, worse than never knowing at all. The people who will be alive in 2880, if civilization endures, will look back at us The way we look back at the people who knew about the approaching Black Death and did nothing. Or the people who saw the levees weakening and chose not to repair them. Or the engineers who warned about the O-rings and were overruled. They will ask the same question we ask you knew. Why did you not act? And the answer, if we are honest, will be because it was far away, because the probability was low, because we had other problems, because the cost was high, because we assumed someone else would handle it, because we could not agree on what to do, because the present always feels more urgent than the future. All true, all inadequate, all human. But here is the other side of that coin. The same species that produces procrastination and short-sightedness also produces cathedrals and constitutions and scientific revolutions. The same brain that discounts the future also dreams of it. The same civilization that struggles with long-term planning also builds libraries and seed vaults and space telescopes designed to operate for decades. We are not defined solely by our limitations. We are also defined by our aspirations. And among those aspirations is one that has driven human progress since the first cave paintings, the desire to leave something behind, to make the world, or the universe, slightly safer, slightly more understood, slightly more beautiful for those who come after. 1950 DA is an invitation to honor that aspiration, not with panic, not with denial, but with the calm, steady, sustained effort that the threat demands. A precursor mission to characterize the asteroid, a technology development program to mature deflection methods, an institutional framework to sustain the work across generations. These are achievable goals. They are not even particularly expensive by the standards of what nations spend on defense, infrastructure, or entertainment. The cost of a precursor mission to 1950 DA is roughly equivalent to the cost of a single aircraft carrier. The cost of a deflection technology program is a fraction of what the world spends on military research in a single year. The resources exist. The technology exists or can be developed. The science is sound. What is needed is the decision, the commitment, the willingness to look at a dot of light in the sky and say, that is our responsibility. Not because it is convenient, not because it is popular, not because it will win an election, but because it is right. Because the people who will face the consequences of our decision deserve better than our indifference. The night sky does not care about our politics, our elections, our quarterly earnings. The asteroid does not care about our attention spans. The laws of orbital mechanics operate with perfect indifference to human hope, human fear, and human procrastination. The rock will arrive on the date that physics dictates, at the velocity that physics dictates, with the energy that physics dictates. And when it arrives, it will not ask whether we meant to prepare. It will not ask whether we ran out of time. It will not ask whether we were distracted by other things. It will simply hit or miss. And which of those outcomes occurs may depend, in the end, on whether a species that learned to see the future also learned to act on what it saw. There is a particular image that sometimes appears in the dreams of planetary scientists who have spent too many nights staring at orbital diagrams and impact simulations. It is the image of a future historian, living in whatever civilization emerges after a catastrophic impact, poring over the records of the 21st century and discovering that we knew, that we had the data, that we had the technology, or could have developed it, that we had 850 years, and that we did nothing. Not because we lacked the means, but because we lacked the will. Because the present was always more urgent than the future. Because the probability was always too low to justify the cost. Because every generation passed the problem to the next, and the next, and the next, until there were no more generations left to pass it to. That image is not a prophecy. It is a possibility. And the distinction between the two depends entirely on what we do in the decades and centuries ahead. The story of 1950 DA, in its deepest form, is a story about inheritance, about what we leave behind. Every generation inherits a world shaped by the decisions of its predecessors, and every generation, in turn, shapes the world for its successors. We inherited a planet with clean oceans and stable climate from generations that did not have the technology to destroy either. Our successors may inherit a planet with a well-characterized near-Earth object population, mature deflection technology, and institutional frameworks for long-term planetary defense, if we choose to build those things. Or they may inherit a planet with an uncertain threat, untested technology, and no institutional capacity to respond if we choose to defer. The choice is ours, not in some abstract philosophical sense, in a concrete budgetary, programmatic sense. The precursor mission to 1950 DA could be designed, funded, and launched within the next 2 decades for a cost that is a rounding error in the defense budgets of major nations. The Deflection Technology Development Program could begin now, with modest initial investment scaling up as the technology matures. The international frameworks could be negotiated and established within a generation, building on the existing structures of ION and SMPAG. None of this requires a technological miracle. None of it requires a political revolution. It requires only the recognition that some problems are too important to defer, even when they feel too distant to matter. It requires only the modest, unglamorous, unsexy commitment to do a little bit now so that our descendants do not have to do everything later. And if the asteroid misses, if the probability collapses to zero as new data comes in, if 1950 DA sails harmlessly past Earth in 2880, and the whole effort turns out to have been unnecessary, then we will have lost nothing but a small fraction of our resources and gained something priceless. The knowledge that we can think in centuries, that we can plan beyond our own lifetimes, that we can act on behalf of people we will never meet, motivated not by fear but by responsibility. That is not a failure. That is the highest expression of what it means to be a civilized species. The paradox of planetary defense is also a paradox of hope. The very fact that we can identify the threat is evidence that we might be capable of addressing it. The telescopes, the radar systems, the orbital mechanics, the computer models, all of these are products of a civilization that, for all its flaws and short-sightedness, has demonstrated a remarkable capacity for solving problems that once seemed impossible. We eradicated smallpox, we split the atom, we walked on the moon, we mapped the human genome, we built a global communication network that connects billions of minds. Each of these achievements was at some point in history considered impossible, impractical, or too expensive, and each was achieved because a critical mass of people decided that the goal was worth the effort. Planetary defense against 1950 DA requires the same kind of decision. Not a dramatic, world-changing, history-altering decision, a quiet one, a budget line item here, a mission proposal there, a sustained research program, an international agreement. Small steps taken consistently over decades and centuries. Not the stuff of movies, the stuff of civilizations. It is late now. The kind of late where the world outside is quiet and the sky, if you are somewhere dark enough to see it, is full of stars. Thousands of them, millions of them, if your eyes have adjusted, each one a sun, each one surrounded by its own family of worlds, its own debris, its own history of collisions and near misses stretching back billions of years. Somewhere among those points of light, too faint to see with the naked eye, a rock is moving. It is roughly 1.1 kilometers across, an irregular lump of stone and dust, spinning once every 2 hours and 7 minutes. It is traveling at roughly 15 kilometers per second, tracing an elliptical path around the sun that brings it across Earth's orbit periodically. It does not know we are here. It does not know it might hit us. It is just a rock, doing what rocks do, following the path that gravity carved for it 4.5 billion years ago when the solar system was young and the planets were still forming from a disk of gas and dust. The rock is called 1950 DA. It was found in 1950, lost for half a century, and found again on the last night of the year 2000. Its orbit carries it past Earth every few years, sometimes close, sometimes far, each passage slightly different from the last because of the tiny, accumulating effects of heat radiation and the gravitational tugs of planets. On the 16th of March in the year 2880, that orbit may bring it to the exact point in space where Earth happens to be, or it may not. The probability is small, 1 in roughly 8,300, but it is not zero. We started this journey with a question implied by the title, is Asteroid 1950 DA a civilization threat? The answer, after everything we have explored tonight, is layered. The asteroid itself is a physical threat, yes. A 1-kilometer impactor carrying 60,000 megatons of kinetic energy, is capable of ending the organized human civilization that exists today. The impact winter, the crop failures, the collapse of infrastructure and supply chains, the cascading failures of interconnected systems that sustain billions of lives, all of this is within the range of peer-reviewed impact modeling. The threat is real, but the deeper threat is not the rock. The deeper threat is the gap between what we know and what we do, the gap between our ability to detect the danger and our willingness to address it, the gap between the 850 years of warning we have been given and the near-total absence of preparation we have undertaken. That gap, not the asteroid, is the civilization threat. Because if we cannot respond to a warning this clear and this early, then we are vulnerable not just to 1950 DA, but to every slow-moving, long-horizon threat that the universe or our own ingenuity might produce. The asteroid spins through the darkness, held together by forces we do not fully understand, on a path we cannot yet predict with the precision we need. It carries no malice. It poses no ultimatum. It simply exists, a leftover from the birth of the solar system, a remnant of the same process that created the Earth and every living thing on it. We and the asteroid are made of the same material, forged in the same stellar furnaces, shaped by the same gravitational forces. We are, in a sense, relatives, children of the same cosmic process, separated by 4.5 billion years of divergent evolution, one branch becoming life and the other remaining rock. And now, after all those billions of years, those two branches may converge, on a single date, in a single moment, on a collision or a near miss, that will determine whether the story of intelligent life on Earth continues or pauses for another few million years until something new arises to try again. If you could shrink the solar system down to the size of a football field, Earth would be a tiny blue marble about 1 centimeter across, sitting on the 27-yard line. 1950 DA would be a grain of fine sand, barely visible, somewhere out past the 50-yard line, moving slowly across the field on a path that curves back toward the marble every few laps. The collision, if it happens, would be like that grain of sand striking the marble at the speed of a bullet. At that scale, the devastation is invisible, a puff of dust, a microscopic scar, but at full scale, that puff of dust is an impact winter. That microscopic scar is a crater 20 kilometers wide, and the marble is your home. We have 850 years. That is more warning than any species has ever had for any threat. The dinosaurs had none. The trilobites had none. The creatures of the Permian extinction, the worst mass extinction in Earth's history, had none. We have 850 years, a fleet of telescopes, a growing catalogue of near-Earth objects, a tested deflection technology at small scale, the mathematical frameworks to plan a mission, and the engineering heritage of a civilization that has already sent machines to every planet in the solar system. What we do with that advantage is the only question that matters. The asteroid does not care about the answer, but the people who will be alive in 2880 will, and they will know what we decided. They will know whether we used the time or wasted it, whether we saw the threat and acted or saw the threat and looked away, whether the species that learned to read the sky also learned to heed what it found there. The night is quiet, the stars are out, and somewhere among them, too faint to see, a rock is spinning, spinning impossibly fast, held together by forces we do not understand, on a path we cannot yet resolve. It is just a rock, but what we do about it will say everything about who we are. If the sun were a basketball sitting on the goal line of a football field, Earth would be a tiny peppercorn about 26 yards away. The moon would be a pinhead, a couple of inches from the peppercorn. Jupiter would be a walnut on the opposite 40-yard line, and the nearest star, Proxima Centauri, would be another basketball roughly 4,200 miles away, in another city, in another time zone. In that scale model, 1950 DA would be smaller than a grain of pollen, drifting through the vast emptiness between the peppercorn and the walnut, barely detectable, easily overlooked, carrying within its insignificant mass the power to change everything about the tiny, living film on the surface of the peppercorn. That is the scale we are dealing with. That is the absurdity of the threat. A speck in a void, aimed at a speck, with the power to end a civilization that took 4 billion years to build. The universe is not cruel, it is not kind, it is indifferent, And in that indifference lies both the threat and the opportunity. The threat because indifference means no mercy. The opportunity because indifference means no malice either. The asteroid is not coming for us. It is simply traveling along a path. And paths can be changed. The last image tonight is this. Somewhere out there, in the cold silence between the planets, a rock is spinning. It has been spinning for 4.5 billion years, since the solar system was a disk of gas and dust and possibility. It has outlasted every civilization that has ever existed on Earth. It has orbited the sun more times than there are people alive today. It is patient in the way that only dead things can be patient, with the infinite patience of matter waiting for gravity to deliver it somewhere. Whether that somewhere is Earth depends on physics we have not yet fully measured, on forces we have not yet fully understood, and on decisions we have not yet made. The physics will clarify itself in time. The forces will yield their secrets to future instruments. But the decisions are ours, and they will not make themselves. The sky is dark, the stars are silent, and a rock, no larger than a small mountain, is spinning through the void, impossibly fast, held together by the faintest of forces, on a trajectory that might, in 850 years, intersect with the only known home of life in the universe. It is just a rock. But what we do about it will define what we are.